What if the ground beneath your feet is not the oldest story that this world has to tell? What if somewhere far, far beyond the reach of cities and roads and everything you have ever known, there lies a place where time itself was sealed away, not by human hands, but by the slow and indifferent weight of ice? Tonight, we travel to the bottom of the earth, to a continent no one truly owns, where a world older than memory has been waiting in the dark. So before you let your body sink fully into this comfort, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you are listening right now, share your location and local time in the comments. Let others know where in the world this story is reaching tonight. Antarctica. The name itself carries a kind of emptiness. It is derived from the Greek Antarctikos, meaning opposite to the north, a definition built not on what the place is, but on what it is not. It is not the Arctic. It is not inhabited in any lasting human sense. It is not green or warm or welcoming. For most of recorded history, it was not even confirmed to exist. The ancient Greeks suspected something might be down there, a southern landmass to balance the weight of the known continents above. But for 2,000 years it remained a theory, a philosophical placeholder, an abstraction sitting at the bottom of the globes that no one had yet proven accurate. When explorers finally reached it in the early 19th century, what they found was not a land in any recognizable sense. It was a wall, a fortress of ice, wind, and silence so vast and so hostile that even the boldest among them could do little more than circle its edges and mark their coordinates before retreating north. Today, Antarctica is classified as a continent. It is roughly 14 million square kilometres, larger than Europe, nearly twice the size of Australia. And yet, despite its enormity, it remains the least understood landmass on the planet. Not because it is inaccessible, though it largely is, but because nearly everything about it is buried. Beneath an ice sheet that averages over 2 kilometres in thickness and reaches more than 4 kilometres in certain regions, the actual surface of Antarctica has never been seen by human eyes. Not once, not in any era of exploration, empire or satellite imaging. What we know of it comes from indirect measurement, radar pulses sent down through the ice, gravity readings taken from aircraft, seismic reflections analysed by teams of geophysicists working in temperatures that can plunge below minus 80 degrees Celsius. And what those instruments have begun to reveal, slowly and incompletely, is something that does not quite fit the narrative we have been told. In 2023, a team led by Professor Stuart Jamieson of Durham University in England published a study that sent a quiet tremor through the geological community. Using satellite data and ice-penetrating radar, Jamieson and his colleagues identified a vast hidden landscape beneath the ice in a remote region of East Antarctica known as Wilkes Land. This was not a flat and featureless plain, the kind of barren bedrock one might expect beneath a continent that has been frozen for tens of millions of years. It was a terrain of deep valleys and sharply peaked hills, carved by the rivers that had once flowed freely through a land that was warm, forested, and alive. The landscape was estimated to cover more than 30,000 square kilometres, an area larger than Belgium, and it had been preserved in almost perfect condition, untouched by erosion, unaltered by time, sealed beneath ice that moved so slowly it had effectively stood still for over 34 million years. Jamieson described the discovery with a phrase that has since been quoted widely among those who study the deep past. He called it like uncovering a time capsule. And then he said something else, something that lingers longer in the mind. He said that the land beneath the East Antarctic ice sheet is less well known than the surface of Mars. Consider the weight of that statement. Humanity has sent rovers to another planet. We have mapped the craters of the Moon, charted the methane lakes of Titan, and photographed the rings of Saturn in detail, fine enough to distinguish individual ice particles. And yet, beneath our own feet, beneath the ice of a continent that sits on this very earth, there exists a world we have barely begun to see. It is not the scale of the discovery that unsettles, it is the implication. If a landscape this vast, this detailed, this rich in geological memory has been lying hidden beneath the ice for 34 million years, then what else might be down there? What other features, what other formations, what other evidence of a world long vanished might still be waiting to be found? And perhaps more importantly, why has it taken so long for anyone to look? The technology to penetrate ice with radar has existed for decades. Satellite systems capable of detecting subtle surface undulations have been operational since the late 20th century. And yet, Antarctica remains the last continent to yield its secrets. Not because the tools were lacking, but because the questions were never asked with sufficient urgency. There is a strange pattern in the history of human knowledge. We tend to assume that what is hidden must be empty, that what cannot be seen must not be significant. Antarctica has suffered from this assumption for centuries. It was treated as a wasteland, a frozen margin of the Earth, useful only for its weather data, its penguin colonies, and its symbolic role in international treaty law. The idea that it might contain something of genuine historical or geological importance, something that could alter the way we understand the deep past of this planet, was, until very recently, not taken seriously by the mainstream scientific community. The ice was too thick, the cold was too severe, the logistics were too expensive, and so the continent was left largely alone, studied at its edges, probed at a handful of inland stations, but never truly examined with the thoroughness it deserved. And then the instruments began to speak. Not loudly, not all at once, but in fragments and whispers that have been accumulating over the past 2 decades. Radar returns showing unexpected topography. Gravity anomalies suggesting dense structures far below the surface. Seismic readings that did not match the simple models of flat cratonic bedrock that had long been assumed. Piece by piece, the image of what lies beneath the Antarctic ice has been changing. And the more it changes, the harder it becomes to maintain the old assumption, the comfortable, inherited belief that Antarctica is simply a dead place, a frozen blank, a continent with nothing to tell. What Jameson's team found in Wilkes Land was not a single anomaly. It was a beginning, a crack in the door of a room that had been sealed shut for an incomprehensibly long time. The valleys they identified were not the shallow grooves in the rock. They were deep, sinuous channels, some plunging nearly 1,200 metres, carved by the rivers that once carried water through forests of beech and conifer, under skies warm enough to sustain life far richer and more complex than anything the continent hosts today. And these rivers did not vanish gradually. They were buried, quickly relatively speaking, by an ice sheet that descended over the continent like a curtain falling at the end of a performance. The forest did not migrate, the rivers did not dry up. They were simply covered, frozen into place, preserved beneath a weight so immense that even the bedrock beneath them was pushed downward by the load. That weight is still there, and so is the landscape, and so perhaps are things we have not yet imagined. 34 million years is not a number the human mind can hold. It is not a span that can be felt or compared to anything within the frame of lived experience. The oldest known civilizations stretch back perhaps 10,000 years. The earliest anatomically modern humans appeared roughly 300,000 years ago. The entire genus Homo in all its forms has existed for no more than 2 or 3 million years. 34 million years ago, there were no humans, there were no great apes, there were no ice caps at either pole, and Antarctica, that white silence at the bottom of every map, was green. Not merely green in the way a tundra is green for a few weeks each summer. Green in the way a rainforest is green. Dense, layered, teeming with life, fed by rivers that ran wide and unhurried through valleys now buried beneath kilometres of ice. The fossil record is unambiguous on this point. Leaf impressions recovered from exposed sediments on the Antarctic Peninsula and on Seymour Island a small wind-battered outcrop off the northeastern tip of the peninsula, show that the continent was once home to forests of southern beech, ancestors of the trees that still grow today in Patagonia and New Zealand. There were conifers, ferns, mosses, there were flowering plants. Pollen samples extracted from sediment cores drilled through the ocean floor around Antarctica confirm a diversity of vegetation that would not look out of place in the temperate forests of modern Chile or Tasmania. But this was not a recent condition. Antarctica had been warm, or at least habitable, for hundreds of millions of years. To understand how it became the frozen desert it is today, it is necessary to go back much further, to a time when the continent was not a continent at all, but a central piece of something far larger. Gondwana. The name comes from a region in central India, the Gond Kingdom, where geologists in the 19th century first identified rock formations that seemed to match those found on other southern continents. It was one of the earliest clues that the land masses of the southern hemisphere had once been joined. Over the following century, the theory of continental drift and later plate tectonics confirmed what those Indian rocks had hinted at. For hundreds of millions of years, the southern continents, South America, Africa, India, Australia and Antarctica, were fused together into a single enormous landmass. Gondwana was not static. It moved slowly across the surface of the Earth, its position shifting over geological time, its climate changing with latitude and atmospheric composition. But throughout much of its existence it was warm. Warm enough for forests, warm enough for rivers, warm enough for life on a scale that is difficult to reconcile with the frozen emptiness that Antarctica presents today. During the Mesozoic era, the age of dinosaurs, Antarctica sat closer to the South Pole than it does now, but it was still connected to other land masses, and the global climate was far warmer than anything in recent geological history. There were no permanent ice sheets anywhere on Earth. The oceans were higher, the atmosphere richer in carbon dioxide, and the polar regions, while cooler than the tropics, were not frozen. Fossil evidence from Antarctica itself confirms this. Dinosaur bones have been found on James Ross Island near the Antarctic Peninsula. Not fragments or ambiguous trace fossils, but identifiable remains of species that lived and died on a continent that was, at the time, a functioning ecosystem. Hadrosaurs, ankylosaurs, theropods. These were not small marginal creatures clinging to the edge of survival. They were large active animals that required substantial vegetation and stable temperatures to sustain their populations. And they were not alone. The forests they moved through were complex. Understories of ferns and cycads, canopies of araucaria, the monkey puzzle tree, a genus that still survives in South America and Oceania, a living echo of a world that has otherwise vanished. Insects pollinated flowers, streams carried sediment through floodplains. The soil was rich, dark, alive with microbial activity. This was not a marginal environment. It was a full functioning biosphere, connected by land bridges to the rest of Gondwana, fed by ocean currents that carried warmth from the tropics to the poles. And then Gondwana began to break apart. The process was not sudden. Continental rifting occurs over tens of millions of years, driven by convection currents deep within the Earth's mantle. South America began to separate from Africa around 130 million years ago. India broke away and began its long northward journey toward Asia. Australia started to pull away from Antarctica roughly 80 million years ago, though the two remained connected by a narrowing land bridge for millions of years after the initial rift. Each separation altered the flow of ocean currents, redirected atmospheric patterns, and changed the distribution of heat across the planet's surface. But none of these separations, dramatic as they were, produced the catastrophic result that the final one did. The critical event was the opening of the Drake Passage, the narrow and violent stretch of ocean that now separates the southern tip of South America from the northern tip of the Antarctic Peninsula. The timing of this event is still debated. Some studies place it as early as 41 million years ago. Others argue it was not fully open till around 34 million years ago, coinciding almost exactly with the onset of Antarctic glaciation. What is not debated is the consequence. Once the Drake Passage opened, a continuous ocean current could flow, unimpeded by any landmass, around the entire circumference of Antarctica. This current, the Antarctic Circumpolar Current, the most powerful ocean current on Earth, effectively walled the continent off from the warmer waters to the north. Heat that had once reached Antarctica's shores was redirected. The continent, now isolated at the bottom of the world, began to cool. But cooling alone does not explain what happened next. The transformation of Antarctica from a forested, river-laced landmass into a frozen wasteland was not a gradual dimming. It was, by geological standards, shockingly fast. Ice cores and marine sediment records suggest that the East Antarctic ice sheet formed within a span of roughly 100,000 years. A blink in geological time. Forests stood for millions of years were buried. Rivers that had carved valleys for epochs were skeletonized. The entire biosphere of a continent was entombed beneath a sheet of ice that would grow to contain roughly 26.5 million cubic kilometers of frozen water. Enough, if melted, to raise global sea levels by more than 50 meters. What kind of event produces that? Not just cold, not just isolation. Something else was happening in the atmosphere. Something that tipped the balance from gradual cooling to runaway glaciation. The leading hypothesis points to a dramatic drop in atmospheric carbon dioxide levels, possibly triggered by increased weathering of silicate rocks exposed by tectonic uplift. As CO2 fell below a critical threshold, estimated at around 750 parts per million, roughly twice the current level, the planet crossed a tipping point. Polar temperatures dropped below the threshold needed to sustain permanent ice, and once the ice began to form, it accelerated its own growth. White ice reflects sunlight. Reflected sunlight means less heat absorbed. Less heat means more ice. The feedback loop, once triggered, was nearly impossible to reverse. And so the world beneath went dark, not destroyed but hidden. The rivers stopped flowing, but their valleys remained. The forests died, but the shapes they had grown among, the ridges, the slopes, the floodplains, were preserved beneath the ice like a death mask pressed against the face of a vanished age. For 34 million years that landscape has lain in silence, unseen, unmeasured, unknown, until now, until the instruments began to listen, until someone thought to look not at the ice but through it. But here is the question that lingers. If the freezing of Antarctica was so rapid, so total, so absolute, then what exactly was sealed beneath the ice in those first violent centuries of glaciation? The rivers are there, the valleys are there, the shape of a living world is there, but is that all? Or did the ice capture something more? Something that the slow, patient work of radar and satellite and seismic survey has not yet been able to reach? There is a boundary in the geological record that scientists refer to with clinical precision. They call it the Eocene-Oligocene transition, and they date it to approximately 33.9 million years ago. In the language of stratigraphy, it is simply a line, a change in sediment composition, a shift in oxygen isotope ratios, a recalibration of the chemical signatures preserved in the shells of microscopic marine organisms called foraminifera. But behind that clinical language lies something far more visceral. The Eocene-Oligocene boundary marks the moment when Antarctica died. Not the rock, not the continent itself, but everything that had lived upon it, everything that had grown and breathed and moved through its forests and along its rivers for hundreds of millions of years. All of it was extinguished within a geological instant, and the silence that followed has lasted ever since. The evidence for this transition comes primarily from ocean sediment cores. long cylinders of mud drilled from the seafloor around Antarctica and in the Southern Ocean. These cores contain layers of material deposited over millions of years, each layer a page in a book that records the chemistry of the ocean, the temperature of the water, the composition of the atmosphere, and the types of organisms that lived and died in that water at any given time. When researchers examine the sediments deposited just before and just after the Eocene-Oligocene boundary, the change is stark. Oxygen isotope ratios in foraminifera shells shift dramatically, indicating a rapid cooling of deep ocean waters and, by extension, a rapid accumulation of ice on the Antarctic continent. The shift is so abrupt in some cores that it appears to have occurred within fewer than 100,000 years, possibly within as few as 40,000. In a geological context, where processes typically unfold over millions of years, this is almost instantaneous. But what does instantaneous mean when applied to the death of an entire continental ecosystem? 40,000 years is still a span that dwarfs all of human civilization. And yet, for a biosphere that had endured for hundreds of millions of years, it was nothing. The forests of southern beach and Araucaria that had blanketed much of the continent did not have time to adapt. There was no slow migration northward, no gradual thinning at the margins. The fossil record shows a collapse, a transition from diverse, complex vegetation to barren ground in a handful of stratigraphic layers. Pollen samples from drill cores taken near the Ross Sea shelf show a sharp decline in tree pollen, and a corresponding rise in cold-adapted mosses and grasses, followed by nothing. Just ice-rafted debris and the chemical signature of a frozen ocean. The animals vanished too. The dinosaurs had already been gone for 30 million years by the time Antarctica froze, wiped out by the Cretaceous extinction event 66 million years ago. But the continent had not been empty in the intervening period. Mammals had colonized it. Marsupials specifically, relatives of the opossums and possums that still inhabit South America and Australia. Fossil remains of marsupial species have been found on Seymour Island, dating to the Eocene, the epoch that immediately preceded the Great Freeze. These were not large animals, not apex predators, but they were present, part of a functioning food web that included birds, insects, freshwater fish, and a rich invertebrate community. When the ice came, they disappeared, not gradually, not through competition or disease or any of the usual mechanisms of extinction. They simply ceased to exist on that continent, their lineage surviving only on the land masses that had already separated and drifted north, Australia and South America, where their descendants live today in forms that carry no memory of the frozen South. There is something deeply unsettling about the speed of this transformation. We are accustomed to thinking of geological change as slow, patient, almost gentle in its inexorability. Mountains rise over millions of years. Oceans open over tens of millions. Species evolve across hundreds of thousands of generations. But the glaciation of Antarctica defied this rhythm. It was, by every measurable standard, a catastrophe. Not in the human sense of the word, not a disaster with victims and rescuers, but in the older Greek sense, catastrophe, an overturning, a reversal so complete that the world before it and the world after it are almost unrecognizable as the same place. And the reversal was not merely biological, it was hydrological, atmospheric, geological. The rivers that had carved the valleys discovered by Jameson's team in Wilkes Land did not simply slow and freeze. They were buried under a weight so immense that the bedrock beneath them was depressed by hundreds of meters. The continent, already sitting at the South Pole, sank further under the load of its own ice. The atmosphere above it dried out. Cold air holds less moisture than warm air, and as temperatures plummeted, snowfall actually decreased. But the snow that did fall never melted. It accumulated, compacted, turned to firn, then to ice, layer upon layer, year upon year, millennium upon millennium, until the ice sheet reached a thickness that would take modern aircraft several minutes to ascend through. What is remarkable, what is in fact nearly miraculous, is that the landscape beneath this ice was not destroyed. Glaciers, as a rule, are erosive. They grind rock, carve fjords, reshape entire mountain ranges. The glaciers of Scandinavia and North America during the Pleistocene ice ages sculpted the terrain of those regions so thoroughly that the landscapes we see today, the Great Lakes, the fjords of Norway, the U-shaped valleys of Scotland, are almost entirely products of glacial erosion. But East Antarctica is different. The ice there is so cold, so thick, and so slow-moving that it has acted not as a sculptor but as a preservative. The base of the East Antarctic ice sheet in many regions is frozen to the bedrock. There is no sliding, no grinding, no meltwater lubricating the interface between ice and rock. The ice simply sits, enormous and still, pressing down on a surface it has not touched in 34 million years. This is why Jameson's discovery was so extraordinary. The river valleys he identified were not remnants, not faded impressions worn down by millennia of glacial abrasion. They were intact. The ridges were sharp. The valleys were deep. The meanders of ancient riverbeds were still legible in the radar data, as clear and defined as if the rivers had stopped flowing yesterday. The ice had not erased the past. It had embalmed it. And the embalming had been so thorough, so perfect, that the landscape beneath East Antarctica is, in many respects, better preserved than landscapes on the surface that have been exposed to wind, rain, and biological activity for the same period of time. This preservation raises a question that is rarely asked in the scientific literature, but that sits quietly beneath every paper and every data set and every radar survey that has been conducted on the continent. If the landscape is preserved, truly preserved, in the way that Jameson's team has demonstrated, then what else might be preserved down there? Not just the shape of valleys and the curve of riverbeds, but the material within them. Sediments, organic matter, the chemical traces of a biosphere that was buried alive, and if those traces exist, if they are sitting beneath the ice in a state of preservation unmatched anywhere else on Earth, then Antarctica is not merely a geological curiosity, it is an archive, a record of a world that vanished so quickly and so completely that almost nothing of it has survived on the surface. The question is not whether the archive exists. The radar data has already answered that. The question is what it contains, and whether we are prepared to read it. But before that question can be addressed, there is another discovery that must be considered. One that came not from the surface of the ice, not from the sediment beneath the ocean floor, but from deep within the bedrock itself. A structure so large, so geometrically coherent, and so unexpected that the team who found it had not even been looking for it. They had been looking at something else entirely, and what they found instead was a pattern that should not, by any conventional understanding of Antarctic geology, exist. In the summer of 2026, a paper appeared in Nature Geoscience that received far less public attention than it deserved. The lead author was Egidio Armadillo, a geophysicist at the University of Genoa in Italy, and what he and his colleagues had found was not a single feature or a localized anomaly, but a continent-scale structure hidden beneath the East Antarctic ice sheet. A structure so vast and so geometrically regular that it challenged several assumptions about how the bedrock of Antarctica was formed. They called it the East Antarctic Fan-Shaped Basin Province. The name itself was an understatement. What the data revealed was a network of approximately 30 enormous basins, each one a depression in the bedrock tens or hundreds of kilometers across, and all of them arranged in a pattern that radiated outward from a single point near the geographic South Pole, like the ribs of an opening fan. The structure extended across a staggering portion of the East Antarctic interior, underlying roughly half of the entire ice sheet. Its outer edge reached toward the coast along a front more than 2,000 kilometers wide, and it had been there, invisible and unsuspected for as long as anyone had been studying the continent. Armadillo's team had not set out to find it. Their original objective was more modest, to reconstruct what East Antarctica would look like if the ice were removed. This is not a simple matter of subtracting ice from a map. The weight of the ice sheet depresses the bedrock beneath it, pushing it downward by hundreds of meters in some areas, more than a kilometer in others. If the ice were to disappear, the bedrock would slowly rebound, a process called isostatic adjustment, and the resulting landscape would be significantly different from the one currently buried under the ice. By combining radar surveys, gravity measurements, seismic data, and magnetic readings, Armadillo's team built a model of this rebounded topography, a portrait of the continent as it might appear after the ice was gone and the rock had finished rising. And that was when the pattern emerged. As the team examined their reconstructed maps, they noticed that the major subglacial basins, features that had been individually catalogued over decades of survey work, were not randomly distributed. They were aligned, not in parallel lines, not in concentric rings, but in a radial arrangement fanning outward from a common centre. The geometry was too coherent to be coincidental. It suggested a single unified process, something that had acted on the crust of East Antarctica at a continental scale, deforming it in a systematic way that left this enormous fingerprint hidden beneath the ice. The team considered several possible explanations. Basins can form through many mechanisms: glacial erosion, tectonic rifting, crustal stretching, inherited weaknesses in ancient rock. But none of these, applied individually, could account for the radial symmetry of the pattern. Glacial erosion tends to produce linear features, valleys, troughs, channels carved in the direction of ice flow. Tectonic rifting creates parallel grabens, elongated depressions bounded by faults on either side. Neither process naturally produces a fan. The geometry pointed instead to something called rotational extension, a process in which the crust spreads outward from a fixed pivot point, like a hand opening slowly from near a fist. The ridges between the basins would be the remnants of crust that held firm while the basins themselves were pulled apart, thinned, and dropped. If this interpretation is correct, and the data published in Nature Geoscience supports it strongly, then the implications are profound. The fan-shaped province may represent a phase of tectonic activity that predates the breakup of Gondwana itself. It may be a scar from one of the earliest episodes of crustal deformation that eventually led to the separation of Antarctica and Australia, a process that began roughly 80 million years ago but may have had precursors stretching back much further. The structure might, in other words, be a relic of the forces that tore a supercontinent apart, preserved not on the surface, where erosion and weathering and biological activity would have long since erased it, but beneath the ice, where nothing has moved and nothing has changed for tens of millions of years. There is a certain irony in this. The ice that buried Antarctica, that killed its forests and silenced its rivers, and erased it from the living world, is also the thing that preserved the evidence of its deepest geological past. Without the ice, the fan-shaped province would likely have been worn away by the same processes that reshape every other continent on Earth. Rain, wind, root systems, freeze-thaw cycles, the slow chemical dissolution of rock by water and organic acids. All of these forces would have attacked the structure over the millions of years since it formed, softening its edges, filling its basins with sediment, obscuring its geometry until it was unrecognizable. But the ice stopped all of that. It froze the evidence in place, literally, and kept it waiting. For what and for whom is a question that the data cannot answer. What the data can tell us is that the structure is not inert. The shape of the bedrock beneath the ice influences the behavior of the ice above it. Ice flows downhill, guided by gravity and by the contours of the surface it rests upon. The basins of the fan-shaped province act as channels directing the flow of ice toward the coast, controlling the speed and direction of glacial movement across half of East Antarctica. This means that a structure formed hundreds of millions of years ago by forces that predate the existence of ice on this continent is still actively shaping the way the ice sheet behaves today. The past is not merely preserved beneath the ice, it is governing the present. And this raises a further question, one that connects Armadillo's discovery to Jameson's and to the broader mystery of what lies beneath the Antarctic ice. If the fan-shaped province is real, if it is a genuine tectonic structure of the scale and age that the data suggests, then the conventional picture of East Antarctica as a simple, stable craton needs to be revised. A craton is a block of ancient continental crust, typically billions of years old, that has remained geologically quiet for most of its existence. East Antarctica has long been assumed to be one of the most stable cratons on Earth, a cold, dead core of Precambrian rock, undeformed since the Archean Eon, the kind of crust that forms the deep foundations of continents and never changes. But a fan-shaped basin province spanning thousands of kilometres is not a feature of a stable craton. It is a feature of a crust that has been pulled, stretched, and reorganised by forces powerful enough to deform an entire continent. What were those forces? When did they act? And what else did they create or destroy in the process? The answers to these questions are still buried, along with everything else beneath the ice. But the fact that the questions are now being asked at all represents a shift in how Antarctica is understood. It is no longer sufficient to treat the continent as a frozen blank, a geological afterthought, a place where nothing of interest lies beneath the surface. The ice is not a wall, it is a vault. And the vault, it turns out, is far more full than anyone had assumed. There is another aspect of the fan-shaped province that deserves attention, though it is rarely discussed in the published literature. The pivot point of the fan, the central node from which the basins radiate, sits near the geographic South Pole. This may be a coincidence of geometry and projection, or it may not. The South Pole is not a fixed point in geological time. The continent has moved over the surface of the Earth, carried by tectonic forces, and its position relative to the pole has shifted over hundreds of millions of years. But the alignment is striking, and it invites a question that no one has yet answered satisfactorily. Was the fan-shaped province influenced by the rotational dynamics of the Earth itself? Did the forces that created it have anything to do with the planet's spin, its axial tilt, the deep mantle convection patterns that drive the motion of tectonic plates? The structure is there, the geometry is clear, but the explanation remains incomplete, and incomplete explanations have a way of concealing the most important truths. Somewhere beneath the ice, in the sediments that fill those 30 basins, there may be a record, a chemical, mineralogical, isotopic record of what happened when the fan opened, a record of the forces, the timing, the sequence of events that deformed half a continent. And if that record exists, it has been sitting there, undisturbed and unread, for longer than most mountain ranges on Earth have existed. The rock remembers what the ice does not. This is the paradox that has shaped Antarctic paleontology for over a century. The fossils that survive on the continent do not come from beneath the ice sheet, where the greatest secrets are likely buried, but from the narrow margins where ancient stone is still exposed to the air. These outcrops are rare, scattered, and brutally difficult to reach. They exist mostly along the Antarctic peninsula and on a handful of islands in the Weddell Sea, places where tectonic uplift or glacial retreat has pushed ancient sediment above the surface just long enough for wind and cold to strip away the covering layers and reveal what lies within. And what lies within, in certain places, is astonishing. Seymour Island is perhaps the most important of these windows into Antarctica's past. It is a small crescent-shaped island lying just off the northeastern tip of the Antarctic peninsula, roughly 64 degrees south latitude. It is treeless, wind-scoured and bar-blanketed in so for much of the year. It does not look like a place that would hold the key to anything, but the sedimentary formations exposed along its ridges and slopes span a period of roughly 70 million years, from the late Cretaceous through the Eocene, and they contain one of the most complete fossil records of any site in the Southern Hemisphere. It was here in the 1980s and 1990s that Argentine and American paleontological teams began to uncover the bones of creatures that had no business being in Antarctica, at least not according to the simplified version of history that most people carry in their minds. They found the remains of large marine reptiles from the Cretaceous, mosasaurs and plesiosaurs that had hunted in the shallow seas around the continent when it was still connected to South America. They found the bones of birds, not penguins but flying birds, ancestors of modern waterfowl and shorebirds, species that had lived on a coastline vastly different from the one that exists today. They found sharks' teeth, the shells of ammonites, the calcified remains of ancient corals, and then, in the layers dated to the Eocene, the last epoch before the Great Freeze, they found something that altered the scientific understanding of what Antarctica had been. They found marsupials, not one species but several. The fossils were fragmentary, jawbones, teeth, partial limbs, but they were unmistakable. These were animals related to the marsupials of South America, small omnivores and insectivores that had crossed the land bridge connecting the two continents sometime during the early Cenozoic, when the passage was still above water and the forest still stood. Their presence on Seymour Island confirmed a hypothesis that had long been debated but never proven, that Antarctica had served as a biological bridge between South America and Australia, a pathway along which marsupials had migrated eastward, reaching Australia before the final separation of the continents severed the connection permanently. The marsupials of Australia, the kangaroos, the wombats, the koalas, owe their existence to a journey that passed through Antarctica, a journey through forests that no longer exist, across rivers that no longer flow, over a land that no longer breathes. But the fossils tell more than just the story of migration. They tell the story of richness. The Eocene sediments on Seymour Island contain an ecological snapshot of a world in its final flourishing, a world that did not know it was about to end. The diversity of plant pollen found in these layers indicates forests of Nothofagus, southern beech, mixed with podocarp conifers, tree ferns, and a variety of flowering plants. The insect record, though less well preserved, suggests a complex web of pollination and decomposition. Freshwater mollusks indicate streams and ponds. The overall picture is one of a temperate forest ecosystem, similar in structure and diversity to the modern forests of southern Chile or the west coast of New Zealand's South Island. A cool, wet, green world alive with the hum of biological activity. And then it ends. In the Eocene-Oligocene transition layers, the pollen record collapses, the leaf fossils disappear, the marsupial bones cease. What replaces them is a cold, sterile signature, ice-rafted debris, glacial sediments, the chemical markers of a continent being buried under ice. The transition on Seymour Island is not as abrupt as it appears in some ocean cores. There is evidence of a gradual cooling through the late Eocene, a slow narrowing of the range of species, a retreat of the warm climate indicators toward the coast. But the final phase, the actual onset of glaciation, is swift and total. Within a handful of stratigraphic layers, representing perhaps a few tens of thousands of years, the biological record simply stops. What is haunting about this is not the extinction itself. Extinctions are common in the geological record, and the mechanisms that drove the Antarctic freeze are well understood in outline, if not in every detail. What is haunting is the completeness of the erasure. on every other continent, the fossil record is continuous. It stretches from the present back through millions of years, layered in sediment, exposed by erosion, accessible to anyone with a shovel and the patience to dig. But in Antarctica, the record ends at the Eocene. Everything that has happened on that continent since the ice arrived, everything that might have been deposited in the sediment, everything that might have been preserved in the rock, is locked away, not destroyed, not eroded, locked, sealed beneath kilometres of ice that has never melted, never retreated, never released its grip on the land beneath. This is what makes the discoveries of Jameson and Armadillo so significant. The radar surveys that revealed the hidden landscape beneath Wilkes Land and the fan-shaped basin province are not simply mapping rock, they are mapping the floor of a sealed chamber. A chamber that contains not only the geological record of a continent's deep past, but potentially the biological and climatic record of the last 34 million years. Sediments that accumulated in those buried valleys before the ice arrived may contain pollen, spores, organic molecules, even microbial DNA. Sediments that formed at the base of the ice sheet itself from the grinding of rock against rock or the slow deposition of particles from subglacial water may contain chemical signatures that could reconstruct the temperature, the atmospheric composition, and the biological activity of a continent that has been assumed for centuries to be dead. The assumption of death is perhaps the most dangerous assumption of all. It is comforting in a way to think of Antarctica as a place where nothing happens, a white, sterile silence at the bottom of the world, a place where the only changes are the slow accumulation of snow and the imperceptible creep of glaciers toward the sea. But comfort and truth are not always the same thing. The fossils on Seymour Island tell us that Antarctica was once a place of extraordinary vitality. The radar data from Wilkes Land tells us that the physical infrastructure of that vitality, the rivers, the valleys, the terrain that supported it, still exists beneath the ice. And the fan-shaped basin province tells us that the geological forces that shape the continent are far more complex, far more dynamic, and far more poorly understood than anyone had assumed. There is a gap in the record, a gap that stretches across 34 million years and an entire continent. And gaps in the study of history, whether human or geologically, are rarely empty. They are filled with the things that were not recorded, the things that were not preserved, the things that were deliberately or accidentally hidden from the future. The ice of Antarctica is the largest gap in the geological record of this planet. And the question that every fossil, every radar return, every isotope ratio leads back to is the same one that has haunted this continent since the first explorer set foot on its shores. What is down there? What has the ice been keeping? And what will happen when, inevitably, the vault begins to open? That question is not entirely hypothetical, because deep within the ice itself, not beneath it but within it, there are records of a different kind, records not of the land but of the atmosphere. Tiny bubbles of ancient air trapped in the ice as snow compacted into crystal over thousands and millions of years. And in one remote corner of East Antarctica, those bubbles have been telling a story that no one expected to hear. A story that stretches back not 34 million years, but 3 million, and that raises its own set of uncomfortable questions about what the Earth's atmosphere was doing while the ice above it grew thicker, and the world below it remained sealed in darkness. Ice is not simply frozen water, it is frozen time. Every snowflake that falls on Antarctica carries within it a small sample of the atmosphere, traces of the gases that surrounded it as it formed, particles of dust swept up from distant continents, microscopic droplets of seawater lofted by storms over the Southern Ocean. When that snowflake lands on the ice sheet and is buried by subsequent layers, it is compressed slowly over centuries and millennia into dense glacial ice. And as it compresses, It traps tiny bubbles of air, sealed capsules of the atmosphere as it existed at the moment the snow fell. These bubbles are not metaphors. They're not approximations. They are the actual air of the ancient world, preserved in crystal, waiting to be opened and read. For decades, the primary tool for reading this atmospheric archive has been the ice core, a long, cylindrical column of ice drilled vertically downward through the ice sheet and extracted for analysis. The most famous of these cores come from sites in central East Antarctica, where the ice is deepest and the accumulation rate is lowest, allowing the record to stretch furthest back in time. The Vostok ice core, drilled by a Soviet and later Russian team beginning in the 1970s, reached a depth of 3,769 meters and yielded a climate record spanning roughly 420,000 years. The Epicodome C core, completed in 2004 by a European consortium, extended the record to 800,000 years. These cores have provided some of the most important data in the history of climate science, revealing the rhythmic oscillation of ice ages and warm periods driven by variations in Earth's orbit, and establishing the tight correlation between atmospheric carbon dioxide levels and global temperature that has become central to the modern understanding of climate change. But 800,000 years, as deep as it is by human standards, is still only a fraction of the time that Antarctica has been frozen. The ice sheet is at least 34 million years old. The cores at their deepest penetrate less than 1% of that history. The rest is inaccessible, buried too deep, too compressed, too deformed by the slow plastic flow of ice under pressure to yield coherent stratigraphic data. Or so it was assumed. In April 2026, a team led by Julia Marks-Peterson, a doctoral student at Oregon State University, and Sarah Shackleton, then at Princeton and now at Woods Hole Oceanographic Institution, published a paper in Nature that pushed the atmospheric record far beyond the limit of any ice core drilled from the top down. They did this not by drilling deeper, but by going to a place where the deep ice had been brought to the surface, a place where the internal dynamics of the ice sheet had taken ancient layers, buried for millions of years, and pushed them upward and outward until they were exposed at the surface like pages of a book forced open by pressure from the spine. The place was Allen Hills, a cluster of nunataks, rocky peaks protruding through the ice in the Transantarctic Mountains, roughly 200 kilometers from the coast of the Ross Sea. Allen Hills is known primarily as one of the world's richest sites for meteorite collection, because the combination of ice flow patterns and fierce winds strips away surface snow and exposes objects that have been carried by the ice from the continental interior over millions of years. But meteorites are not the only ancient objects that surface at Allen Hills. So does ice. Extraordinarily old ice. Ice that has been transported from deep within the East Antarctic ice sheet by the slow conveyor belt of glacial flow, compressed and folded, and eventually thrust upward along the mountain front until it reaches the surface in a band of blue, bubble-rich crystal that has not seen the sky since long before the first humans walked the Earth. Marks-Peterson and Shackleton's team collected samples of this blue ice and analysed the gas bubbles trapped within it. What they found was a record of atmospheric carbon dioxide and methane levels stretching back approximately 3 million years, far older than any previous direct measurement of ancient air. And the record told a story that was, in some respects, deeply reassuring and in others, deeply strange. The reassuring part was the stability. Over the entire 3 million year span, atmospheric CO2 and methane levels remained broadly stable, fluctuating within a relatively narrow range. This was consistent with the existing understanding of the Pliocene and Pleistocene climate, a period characterized by cycles of glaciation and warming, driven primarily by orbital variations but underlain by a relatively steady baseline of greenhouse gas concentrations. The ice ages came and went, the ice sheets advanced and retreated, sea levels rose and fell by tens of meters, But the fundamental chemistry of the atmosphere did not undergo the kind of dramatic, irreversible shift that had occurred at the Eocene-Oligocene boundary 34 million years earlier. The strange part was what the stability implied. 3 million years ago, during the mid-Pliocene warm period, global temperatures were 2 to 3 degrees Celsius warmer than today. Sea levels were 15 to 25 meters higher. The Arctic was largely ice-free in summer. And yet, according to the Allen Hills data, atmospheric CO2 levels during this warm period were not dramatically higher than pre-industrial levels, perhaps 400 parts per million, comparable to the concentration that human activity has already pushed the atmosphere past in the 21st century. This suggests that the relationship between CO2 and temperature is not as linear or as simple as some models assume. Small changes in greenhouse gas concentrations can, under certain conditions, produce large changes in climate, a sensitivity that has implications not only for understanding the past, but for predicting the future. But there is another dimension to the Allen Hills discovery that has received less attention in the press coverage and the scientific commentary, and it is this dimension that connects most directly to the larger mystery of what lies beneath the Antarctic ice. The ice at Allen Hills is old, 3 million years old in the samples analysed by the Marks Peterson's team, but it is not the oldest ice that exists on the continent. It is simply the oldest ice that has been found at the surface where it can be collected and analysed with current technology. Deeper within the ice sheet, in the vast, slow-moving interior of East Antarctica, there are almost certainly layers of ice that are far older, ice that dates to the Miocene, the Oligocene, perhaps even the earliest phases of Antarctic glaciation. This ice has never been sampled, it has never been analysed. It sits in the dark, compressed by the weight of everything above it, carrying within its bubbles a record of atmospheric conditions that no human instrument has ever measured. The search for this ancient ice is one of the quiet frontiers of Antarctic science. Several international projects, including the European Beyond Epica initiative and a parallel Australian effort, are currently working to identify sites where million-year-old ice might be preserved in stratigraphically coherent layers suitable for core drilling. The challenge is immense. At such depths, the ice has been subjected to millions of years of pressure and flow, and the original layering, the neat chronological sequence of annual snowfall that makes younger ice cores so readable, is often disrupted, folded, or sheared beyond recognition. Finding a site where ancient ice has remained undisturbed, where the layers are still in order, where the bubbles have not been compromised by recrystallization or diffusion, is a task that requires not only advanced geophysical survey techniques, but also a measure of geological luck, and yet the prize is almost beyond calculation. If ice from the Oligocene could be recovered and analysed, ice that was deposited in the first centuries of Antarctic glaciation, when the forests were dying and the rivers were stopping, and the temperature was plunging toward conditions that would persist for the next 34 million years. It would provide a direct physical sample of the atmosphere during one of the most dramatic climate transitions in Earth's history. It would tell us exactly how much CO2 was in the air when the ice began to form. It would tell us how quickly the greenhouse gases changed and in what sequence. It would, in effect, open a window into the very moment when Antarctica's living world was sealed away. That window remains closed, for now, but the ice at Allen Hills has proved that the archive exists, that the atmosphere itself has been preserved, frozen in crystal, waiting beneath the surface of a continent that has kept its secrets longer than any other place on Earth. And if the atmosphere is preserved, then the question that follows is inevitable, and it is a question that reaches beyond chemistry and climate and into a territory that is far more speculative, far more unsettling, and far more ancient than anything the ice cores have yet revealed. Because the oldest maps in human history, maps that should not exist, maps out that depict a world no living civilization should have been able to observe, seem to show a coastline that has been buried under ice for millions of years, and no one has ever adequately explained how. In 1929, a German theologian named Gustav Adolf Deissmann was working in the Topkapi Palace Library in Istanbul when he came across a fragment of a map drawn on gazelle skin parchment. The map was old, dated by an inscription in Ottoman Turkish to the month of Muharram in the year 919 of the Islamic calendar, corresponding to 1513 in the Gregorian system. It was signed by an Ottoman admiral named Haji Ahmed Muhyiddin Piri, known to history as Piri Reis. The fragment showed the western coast of Africa, the eastern coast of South America, and, at the bottom of the parchment, a landmass that curved eastward beneath the Atlantic, a landmass that bore an unsettling resemblance to the northern coastline of Antarctica. The map was remarkable for several reasons. Its depiction of the South American coastline was surprisingly accurate for a document created only 21 years after Columbus's first voyage to the New World. The Caribbean islands were rendered with a level of detail that suggested access to navigational information far more precise than anything available to European cartographers of the early 16th century. Piri Reis himself noted, in annotations written on the map, that he had compiled it from approximately 20 older source maps, including charts used by Columbus, Portuguese navigational maps, and what he described as maps drawn in the time of Alexander the Great, maps that, if they existed, would date to the 4th century BCE or earlier. For decades after its rediscovery, the Piri Reis map was treated as a historical curiosity, an interesting example of Ottoman cartography, notable for its early depiction of the Americas, but not particularly controversial. That changed in 1960 when Charles Hapgood, a professor of history at Keene State College in New Hampshire, published a book called Maps of the Ancient Sea Kings. Hapgood's thesis was provocative. He argued that the Piri Reis map, along with several other medieval and Renaissance-era maps, contained geographical information that could not have been obtained by any civilization known to have existed at the time the maps were drawn. Specifically, he focused on the southern portion of the Piri Reis map, the landmass at the bottom of the parchment, and argued that it depicted the coastline of Queen Maud Land, a region of Antarctica, as it would appear if the ice were removed. Hapgood was not a crank. He held a legitimate academic position, and his methodology, while unconventional, was systematic. He subjected the Piri Reis map and several other historical maps to detailed mathematical analysis, comparing their projections and coordinates to modern geographical data. He corresponded with the United States Air Force, which at the time was conducting its own mapping of Antarctica using advanced aerial survey techniques, and received a response from Lieutenant Colonel Harold Z. Ohlmeyer of the 8th Reconnaissance Technical Squadron, stating that the lower portion of the Piri Reis map appeared to depict the Princess Martha coast of Queen Maud Land, and that the geographical detail shown was remarkably consistent with the subglacial topography of that region as revealed by seismic surveys conducted during the International Geophysical Year of 1957 to 1958. Ohlmeyer's letter, while carefully qualified, concluded that the agreement between the map and the seismic data was notable, and that the cartographic information in the Piri Reis map suggested knowledge of the coastline before it was covered by ice. The implications of this, if taken at face value, are staggering. The coastline of Antarctica has been covered by ice for millions of years. No human civilization known to mainstream archaeology could have observed it, surveyed it, or mapped it. The oldest known civilizations, Sumer, Egypt, the Indus Valley, date to roughly 5,000 years ago, and even the most generous estimates of pre-agricultural human activity do not extend the timeline of organized, technologically capable societies beyond 15 or 20,000 years. 34 million years of ice cover is so far beyond any plausible human presence that the gap is not merely large. It is, within the framework of conventional history, unbridgeable, Hapgood's explanation was a theory he called Earth crust displacement, which proposed that the entire outer shell of the Earth had shifted at some point in the relatively recent past, moving Antarctica from a more temperate latitude to its current polar position. This theory, which Albert Einstein had expressed cautious interest in during correspondence with Hapgood in the 1950s, was never accepted by the mainstream geological community. The mechanism Hapgood proposed, a build-up of ice at the poles creating an asymmetric mass that could cause the crust to slip, was considered physically implausible given what was known about the viscosity of the Earth's mantle and the forces required to move tectonic plates. The theory has been largely set aside by modern geophysics, though it has never been conclusively disproven, and it continues to circulate in alternative history circles as an explanation for anomalous ancient maps and out-of-place archaeological findings. But the dismissal of Hapgood's mechanism did not resolve the central puzzle of the map itself. If the Peary Race map does not depict Antarctica, if the southern landmass is simply a distorted rendering of the South American coastline bent eastward to fit the edge of the parchment, as some cartographic historians have argued, then the mystery dissolves. But if it does depict Antarctica, even approximately, then the question remains, where did the information come from? Peary Race stated that he used source maps of great antiquity. Those source maps, whatever they were, have not survived. The Library of Constantinople, the Imperial Ottoman Archives, the scattered repositories of ancient navigational knowledge that existed in the Islamic world during the 16th century, none of them have yielded any chart matching the description Peary Race provided. The sources, like so many things connected to this story, are lost, and the Peary Race map is not the only one. Hapgood identified several other historical maps that appeared to contain anomalous geographical knowledge. The Orontes Phineas map of 1531 depicts a southern continent with a shape and orientation remarkably similar to Antarctica, complete with mountain ranges and river systems that bear some correspondence to features now known to exist beneath the ice. The Philippe Boichet map of 1737 appears to show Antarctica divided into two landmasses separated by a waterway, a configuration that would be consistent with the subglacial topography of West Antarctica, where the bedrock in many areas lies below sea level, and where, if the ice were removed, much of the region would indeed be submerged. These maps were drawn centuries before the first confirmed sighting of Antarctica in 1820, and they contain details that, if accurate, could not have been obtained by any known method of observation available at the time. The mainstream explanation for these maps is that they represent speculative geography, the cartographic tradition, dating back to the ancient Greeks, of depicting a large southern landmass called Terra Australis Incognita, the unknown southern land, whose existence was inferred on theoretical grounds rather than observed directly. Aristotle and Ptolemy both posited that such a continent must exist to balance the land masses of the Northern Hemisphere, and this belief persisted in European cartography well into the 18th century, long after it became clear that the actual Antarctic continent was far smaller and far more inhospitable than the vast temperate land the ancients had imagined. In this view, the southern landmasses depicted on the Peary Race and Orontes Phineas maps are not based on genuine surveys of Antarctica, but on imaginative extrapolation, educated guesses that happen by coincidence to bear a superficial resemblance to the real thing. This is a reasonable explanation. It may even be the correct one, but it does not quite account for all the details. The river system on the Orontes Phineas map, the subglacial division on the Boichet map, the specific coastal features on the Peary Race fragment that Ohlmeyer's team at the Air Force found consistent with seismic data. Coincidence can explain a great deal, but there is a point at which the accumulation of coincidences begins to resemble something else. Not proof, certainly, but a pattern. A whisper of something that the available evidence cannot confirm but also cannot entirely dismiss. And behind all of these maps, behind Piri Reis and his 20 source charts, behind the speculative geographies of the Renaissance and the theoretical continents of the ancient Greeks, there is a deeper question, one that connects the mystery of the maps to the mystery of the ice and the mystery of the vanished world beneath it. The question is not whether someone mapped Antarctica before it was frozen. The question is whether someone mapped it before the maps we have were drawn. Someone whose knowledge was passed down, copied, translated, corrupted, and eventually preserved in fragments that no longer make sense within the historical framework we have constructed. Because knowledge, like ice, can bury things, and what is buried is not always what we expect to find. The ancient world was not as ignorant as modernity is sometimes preferred to believe. This is not a radical claim. It is not the territory of fringe theorists or alternative historians. It is the quiet consensus of classical scholarship, often overlooked because it complicates the narrative of linear progress that underpins so much of the way history is taught and understood. The Greeks measured the circumference of the earth. The Phoenicians circumnavigated Africa. The Polynesians crossed the Pacific using star maps and wave patterns that modern navigators struggle to replicate. And somewhere, in the libraries and archives of civilizations that have since crumbled to dust, there were maps, charts of coastlines, sea routes and land masses, compiled from voyages that were never recorded in the histories that survived. The most famous of these lost repositories is the Library of Alexandria. Founded in the 3rd century BCE under the Ptolemaic dynasty of Egypt, it was conceived not merely as a collection of books, but as a universal archive, a storehouse of all human knowledge gathered from every corner of the known world. Ships arriving in the harbour of Alexandria were reportedly searched, and any scrolls found on board were confiscated, copied and added to the library's holdings. Envoys were sent to Athens, Carthage, Persia and beyond to purchase or transcribe manuscripts. At its peak, the library is believed to have contained between 400,000 and 700,000 scrolls, encompassing works of philosophy, mathematics, astronomy, medicine, geography, navigation and history drawn from dozens of cultures and languages. The destruction of the Library of Alexandria is one of the great tragedies of intellectual history, though the precise circumstances remain debated. There was no single catastrophic event, no single fire, no single act of vandalism that reduced the entire collection to ash in a single night, despite the popular image. The library appears to have declined over several centuries, damaged by a series of events including Julius Caesar's fire during the siege of Alexandria in 48 BC. The edict of the Roman Emperor Theodosius I in 391 CE ordering the destruction of pagan temples and the gradual erosion of institutional support as the Roman Empire fragmented and the city's political importance waned. By the time the Arab general Amr ibn al-As conquered Alexandria in 642 CE, whatever remained of the library was likely a shadow of its former self. A fraction of a fraction, preserved in scattered collections across the city, much of it already lost to neglect, conflict, and the slow decay of papyrus in the Mediterranean climate. What was lost cannot be fully known because the catalogue itself is lost. But fragments and references in surviving texts give some indication of the scope. The works of Aristarchus of Samos, who proposed a heliocentric model of the solar system 18 centuries before Copernicus, were held in the library. So were the geographical writings of Eratosthenes, who not only calculated the circumference of the Earth with remarkable accuracy, but also served as the library's chief librarian and compiled maps of the known world that were the most comprehensive of their time. The navigational records of Phoenician expeditions, including the reported circumnavigation of Africa commissioned by the Egyptian pharaoh Necho II around 600 BCE, and described by Herodotus, may have been deposited there. And if Peary Race was correct, if the source maps he used to compile his 1513 chart were themselves copies of older charts, passed down through centuries of translation and recopying, then it is not unreasonable to ask whether some of those source maps might have originated in or passed through the Library of Alexandria before it was destroyed. This is not a claim that can be proven, it is a thread, a filament of possibility suspended between what is known and what is lost. But the filament is not as thin as it might appear. The transmission of ancient geographical knowledge through the Islamic world is well documented. Arab scholars of the 8th, 9th and 10th centuries translated and preserved vast quantities of Greek, Persian and Indian scientific writing that would otherwise have been lost. The House of Wisdom in Baghdad, the libraries of Cordoba and Cairo, the scholarly networks that stretched from Samarkand to Seville, these were the channels through which ancient knowledge survived the collapse of the Roman world and the fragmentation of the classical Mediterranean. Maps were part of this transmission. The work of Ptolemy, whose Geographia laid the foundation for European cartography until the Age of Exploration, was preserved and transmitted through Arabic translations. So were the navigational charts of the Indian Ocean, compiled by Arab and Persian sailors who had been trading with East Africa, India and Southeast Asia for centuries before the Portuguese rounded the Cape of Good Hope. Peary Race operated within this tradition. As an Ottoman admiral, he had access to the accumulated navigational archives of the Islamic maritime world. Charts and portolans and route descriptions gathered over centuries of trade and warfare across the Mediterranean, the Red Sea, the Indian Ocean and beyond. He also had access, by his own account, to captured European charts, including maps reportedly taken from a Spanish sailor who had travelled with Columbus. The 20 source maps he claimed to have used in compiling his 1513 chart were drawn from multiple traditions, multiple centuries, and multiple civilizations. And at least some of them, he stated, were very old. Old enough that their origins had been forgotten by the time they reached his hands. The question that Hapgood raised, and that has never been satisfactorily answered, is whether the chain of transmission might extend further back than the classical period. Whether the source maps behind the source maps, the originals behind the copies, behind the translations, behind the fragments, might represent a body of geographical knowledge compiled by a civilization or a culture that predates the historical record as we currently understand it. This is where the discussion crosses from history into speculation, and it is important to be honest about that boundary. There is no direct evidence of a pre-classical civilization capable of systematic cartography. There are no surviving maps that can be definitively dated to a period before the ancient Greeks. The hypothesis rests entirely on inference, on the anomalous details in maps like the Peary Race, the Orontius Phineus, and the Buaja, and on the assumption that these details cannot be explained by coincidence or creative extrapolation alone, and yet the inference is not easily dismissed. Eratosthenes calculated the Earth's circumference around 240 BCE, but his method, measuring the angle of shadows at two different latitudes, required a degree of mathematical sophistication and observational precision that did not spring from nothing. He built on the work of earlier thinkers, some of whose writings survive and many of whose writings do not. The Phoenicians, who were active as maritime traders and explorers for more than 1,000 years before Eratosthenes, left almost no written records of their own. Their libraries, if they had them, were destroyed with Carthage in 146 BCE, and what we know of their voyages comes almost entirely from the accounts of their Greek and Roman rivals. The navigational knowledge of the Polynesians, who settled islands across an ocean covering 1/3 of the Earth's surface, was transmitted entirely through oral tradition and was nearly lost during the colonial period before being partially recovered in the 20th century. If these cultures, the Phoenicians, the Polynesians, and others whose names we may never know, possessed geographical knowledge that was not preserved in writing, or that was preserved in forms that did not survive the destruction of their archives, then the absence of evidence is not evidence of absence. It is simply silence. And silence in the study of the deep past is the most common sound there is. The vast majority of everything that has ever been known, thought, discovered, or recorded by human beings has been lost. The Library of Alexandria is only the most famous example. Libraries burned in Carthage and Persepolis, in Constantinople, in Baghdad, in the temples of the Maya and the monasteries of Tibet. Each fire, each sacking, each slow decay took with it knowledge that can never be recovered, not because it did not exist, but because the vessels that carried it were fragile, and the forces that destroyed them were not. What survived did so by accident as much as by design. A scroll copied one more time before the original crumbled. A map redrawn by an Ottoman admiral who happened to have access to charts that no one else thought to preserve. A fragment of parchment found in a palace library 4 centuries after it was drawn by a theologian who happened to be looking for something else entirely. The Piri race map exists today because of a chain of improbable events, any one of which, had it not occurred, would have consigned the map to the same oblivion that claimed its source materials. And if the map is a survivor, if it is one of the few remaining traces of a body of knowledge that was once far larger and far more detailed, then the question is not only what was lost. The question is what else might have been known, and by whom, and how long ago, and whether any of that knowledge, any trace, any echo, any faint impression might still be recoverable. Not from the libraries which are gone, not from the maps which are fragments, but from the one place on Earth where the past has been preserved on a scale and with a fidelity that no human archive could ever match. The ice that buried a continent, the ice that sealed away a world, the ice that has kept its secrets for 34 million years, and may, beneath its coldest and deepest layers, still hold records that no library was ever large enough to contain. But the ice is not the only thing hiding beneath Antarctica. There is water down there as well, liquid water flowing in darkness, filling lakes that have not seen sunlight since before the first primates appeared on Earth. And what has been found in that water and what is suspected to exist within it raises questions that extend beyond history and geology and into the realm of biology itself. Beneath the surface of the East Antarctic ice sheet, in a darkness so complete that it has not been interrupted by a single photon of sunlight in 15 million years, there is a lake, not a pocket of meltwater, not a thin film of liquid trapped between ice and rock. A lake, a body of fresh water roughly 250 kilometers long, 50 kilometers wide, and in places more than 800 meters deep. It contains an estimated 5,400 cubic kilometers of water, making it comparable in volume to Lake Ontario, one of the 5 Great Lakes of North America. It sits beneath nearly 4 kilometers of ice, held in a liquid state by a combination of geothermal heat rising from the Earth's mantle below and the immense pressure of the ice above, which lowers the melting point of water just enough to prevent the lake from freezing solid. Its name is Vostok, taken from the Russian research station that has operated on the ice surface directly above it since 1957, and it is the largest of more than 400 subglacial lakes that have been identified beneath the Antarctic ice sheet. The existence of Lake Vostok was first hypothesized in the 1960s based on airborne radar surveys that detected a flat, highly reflective surface beneath the ice, a signature consistent with a water ice interface rather than a rock ice one. The hypothesis was confirmed in the 1990s using satellite altimetry and more advanced radar techniques, and it immediately raised questions that have not yet been fully answered. How old is the water? Has it been sealed from the atmosphere since the lake was first covered by ice? What, if anything, lives in it? And if life does exist there? In total darkness, under crushing pressure, in water that has been isolated from the rest of the biosphere for millions of years, what form does it take? The question of life in Lake Vostok is not idle speculation. It is a scientific question with direct implications for fields as diverse as astrobiology, evolutionary biology, and the study of extreme environments. If microorganisms exist in the lake, organisms that have survived in isolation for millions of years, cut off from sunlight, from atmospheric oxygen, from the nutrient cycles that sustain life everywhere else on Earth, they would represent a form of life unlike anything currently known. They would be living fossils in the most literal sense, descendants of organisms that were sealed into the lake when the ice first closed over it, and that have since evolved in complete independence from the rest of the tree of life. Their biochemistry, their genetics, their metabolic pathways would be products of an evolutionary experiment conducted in conditions so extreme that they have no parallel on the surface of this planet. In February 2012, after more than 2 decades of drilling, a Russian team at Vostok station finally penetrated the ice water boundary and obtained samples of water from the lake itself. The results were controversial. Initial analyses detected traces of DNA, but contamination from the drilling fluid, kerosene-based and teeming with surface microorganisms, made it difficult to determine whether the detected sequences originated from the lake or from the equipment used to access it. Subsequent studies using more stringent decontamination protocols identified genetic sequences that did not match any known organism in existing databases, sequences that appeared to represent novel species, possibly unique to the Lake Vostok environment. But the findings remain contested, and the scientific community has been cautious about drawing definitive conclusions from what remains a limited and potentially compromised dataset. What is not contested is that microbial life exists in the ice above the lake, in the so-called accretion ice, a layer of refrozen lake water that has been incorporated into the base of the ice sheet over hundreds of thousands of years. Analyses of accretion ice samples from the Vostok core have revealed bacterial cells, both intact and fragmented, at concentrations of a few hundred to a few thousand cells per milliliter. Some of these bacteria are related to known extremophile groups, organisms that thrive in hot springs, deep-sea hydrothermal vents, and other environments that would be lethal to most life forms. Others are unclassifiable, their genetic signatures too divergent from anything in current databases to assign them to a known taxon. They are, in a very real sense, strangers. Organisms that have been living in a world apart, following their own evolutionary trajectory, for a span of time that exceeds the entire history of the genus Homo by an order of magnitude. Lake Vostok is not alone. The 400 and more subglacial lakes identified beneath the Antarctic ice sheet form a hidden hydrological network, a system of rivers, channels and reservoirs that operates in total darkness, beneath kilometers of ice, driven by geothermal heat and the pressure gradients created by the weight of the ice above. Some of these lakes are connected, linked by subglacial rivers that flow intermittently as water levels rise and fall in response to changes in ice thickness and basal temperature. Others appear to be isolated, sealed off from the rest of the network, each one a self-contained environment with its own chemistry, its own temperature regime, and potentially its own biology. The network is dynamic. Satellite measurements have detected sudden changes in ice surface elevation that correspond to the filling and draining of subglacial lakes, suggesting that water moves through the system in pulses, flowing from one reservoir to another in episodes that can last months or years. This hidden water system has implications that extend beyond biology. Subglacial water lubricates the base of the ice sheet, reducing friction between ice and rock and allowing glaciers to move faster than they otherwise would. The dynamics of ice flow, how quickly ice moves from the interior of the continent toward the coast, where it carves into icebergs and contributes to sea level rise, are directly influenced by the distribution and behavior of subglacial water. Understanding the network of lakes and rivers beneath the ice is therefore critical to predicting how the ice sheet will respond to a warming climate, and the discovery of the fan-shaped basin province by Armadillo's team adds a new layer of complexity to this picture. The 30 basins of the fan-shaped province are not empty depressions. They are potential reservoirs, places where subglacial water could accumulate, flow, and interact with the ice in ways that are not yet understood. And there is a deeper connection still, a connection between the water, the ice, the hidden landscape, and the question of what has been preserved beneath Antarctica for all these millions of years. Water is a solvent. It dissolves minerals, carries nutrients, transports chemical signatures from one place to another. The subglacial water that flows through the buried valleys of Wilkes Land, over the ancient river-carved terrain that Jameson's team discovered, is in contact with sediments that have not been exposed to the atmosphere since the Eocene. Whatever is in those sediments, organic molecules, pollen, spores, microbial remains, the chemical traces of a vanished ecosystem, is being slowly dissolved, transported, and redeposited by water that has been circulating in darkness for millions of years. The lakes are not just habitats for extremophile bacteria, they are archives, collecting and concentrating the chemical memory of a continent that has been sealed away from the rest of the world. Lake Vostok in particular may contain a sediment record of extraordinary value. The lake bed, buried beneath 4 kilometers of ice and 800 meters of water, has never been directly observed, but geophysical models suggest that it's covered by a layer of sediment, possibly meters thick, deposited over millions of years by the slow rain of particles from the melting and refreezing of ice at the lake ceiling, by the influx of mineral-laden water from subglacial streams, and by the biological activity of whatever organisms inhabit the lake. This sediment, if it could be sampled and analysed, might contain a continuous record of conditions at the base of the ice sheet, stretching back to the earliest days of Antarctic glaciation, a record that would complement and extend the atmospheric data preserved in ice cores, and that could reveal details about the transition from a living continent to a frozen one that no other source of data can provide. But reaching that sediment is another matter entirely. The Vostok drilling project took more than 20 years to reach the lake surface, and it did so using techniques that many in the scientific community considered inadequate to prevent contamination. Drilling through 4 kilometers of ice, maintaining sterile conditions, and retrieving uncontaminated samples from a lake that has been sealed for the millions of years is a technical challenge that pushes the boundaries of current engineering. And the stakes are high, not just scientifically, but ethically. If Lake Vostok is a sealed biosphere, a living laboratory that has been running its own experiment in evolution for 15 million years, then breaching it carelessly could destroy the very thing that makes it valuable. The organisms inside adapted to conditions of extreme pressure, darkness, and chemical isolation might not survive exposure to surface contaminants. The chemical signatures preserved in the sediment might be disrupted by the introduction of drilling fluids. The archive might be ruined before it is read. This tension between the desire to know and the risk of destroying what we seek to understand is not unique to Lake Vostok. It runs through the entire history of Antarctic exploration, and it connects, in ways that are not always obvious, to a set of decisions made in the middle of the 20th century that determined how the continent would be governed, who would have access to it, and what could and could not be done there. Decisions that were made in secret by a small number of nations at the height of the Cold War. Decisions that resulted in a treaty unlike any other in the history of international law, a treaty that locked an entire continent away from the normal processes of territorial claim, resource extraction, and military use, and that has remained in force largely unchallenged for more than 6 decades. A treaty that some have called the most successful international agreement ever negotiated, and that others have called something else entirely. Before the treaty there was the expedition, before the diplomacy there was the military, and before the world agreed to leave Antarctica alone, one nation sent a fleet so large and so heavily armed to its shores that the operation remains, to this day, one of the most puzzling chapters in the history of polar exploration. In December 1946, the United States Navy launched Operation High Jump, officially designated Task Force 68, under the command of Rear Admiral Richard Evelyn Byrd, the most famous polar explorer of the 20th century. Byrd was already a legend by that time. He had led the first flights over both the North and the South Poles, established the first permanent American base in Antarctica, Little America on the Ross Ice Shelf, and conducted 2 previous Antarctic expeditions that had mapped vast stretches of the continent's coastline and interior. He was decorated, celebrated, and deeply connected to the military and political establishment of the United States. And in the winter of 1946, the age of 58, he was sent back to the ice with a force that defied any ordinary definition of a scientific expedition. The numbers alone are striking. Operation High Jump comprised 13 ships, including an aircraft carrier, a submarine, 2 destroyers, and several icebreakers. It carried 33 aircraft, helicopters, flying boats, and transport planes, equipped with cameras and mapping instruments. The total personnel numbered approximately 4,700 men, making it the largest Antarctic expedition ever mounted, before or since. The official objectives, as stated by the Navy, were to train personnel for cold weather operations, test equipment in extreme conditions, consolidate and extend American territorial claims in Antarctica, and conduct aerial mapping and photographic surveys of the continent's coastline. These objectives were plausible. The Cold War was beginning. The Soviet Union was expanding its influence and the strategic value of polar regions, as potential corridors for long-range bombing runs, submarine operations, and missile trajectories was well understood by military planners on both sides. Antarctica, though far from any theatre of active conflict, represented an enormous blank space on the geopolitical map, and the United States had a legitimate interest in asserting its presence there. The training rationale was also credible. The Navy had limited experience operating in polar conditions, and the lessons of World War II, which had included campaigns in the Arctic and subarctic, had demonstrated the importance of cold weather readiness. But the scale of the operation exceeded what any of these objectives would reasonably require. Training exercises do not typically involve aircraft carriers. Mapping surveys do not normally require destroyers. And the timeline of the operation, originally planned for 6 to 8 months, was cut dramatically short. Operation High Jump was terminated in late February 1947, after only about 8 weeks, well before many of its stated objectives had been completed. The official explanation was that the approaching Antarctic winter made further operations unsafe. This was true. Antarctic winters are lethal to surface operations, but the decision to launch such a massive expedition so late in the austral summer, with so little time to accomplish its goals, has never been adequately explained. What has drawn the most attention, however, is not the logistics of the operation, but the statements made by Byrd after his return. In a widely cited interview published in the Chilean newspaper El Mercurio on March 5, 1947, Byrd was quoted as saying that the United States would need to prepare for the possibility of hostile aircraft operating from the polar regions, and that the greatest threat to the country might come from the south rather than from any conventional adversary. The precise wording of the interview has been translated differently by different sources, and the context of Byrd's remarks, whether he was speaking literally, metaphorically, or in terms of strategic contingency planning, has been debated extensively. But the general tenor of the statement was clear enough to attract attention at the time and to fuel decades of speculation afterward. The speculation has taken many forms, ranging from the plausible to the fantastical. Some researchers have argued that Operation High Jump was primarily a geopolitical exercise, a show of force intended to deter Soviet interest in Antarctica and establish American military dominance over the continent before any international agreement could limit that dominance. Others have suggested that the operation had intelligence objectives, that the United States was searching for remnants of German military activity in Antarctica, following reports that German U-boats had been spotted in Antarctic waters during and after World War II, and that the Third Reich had maintained a secret base somewhere on the continent. This latter theory, while largely unsupported by declassified documents, is not entirely without basis. Germany did conduct an Antarctic expedition in 1938 to 1939, the Schwabenland expedition, which surveyed and photographed a large area of Queen Maud Land, dropped marker flags from aircraft to claim territory, and named the region Neuschwabenland. The purpose of this expedition was, according to German records, to establish a whaling base and assert territorial claims, but the timing on the eve of World War II and the secrecy surrounding certain aspects of the mission have led to persistent questions about whether the expedition had other undisclosed objectives. What is documented is that Byrd's expedition encountered unexpected difficulties. Several aircraft were lost. At least 3 planes went down during the operation, with the loss of crew members. Weather conditions were severe, even by Antarctic standards. And the aerial surveys, while they did produce thousands of photographs covering portions of the coastline, were far less comprehensive than planned. The maps generated by Operation High Jump were useful but incomplete, and many of the areas targeted for survey were never reached. When the task force returned to the United States in April 1947, the official reports emphasized the accomplishments, the photographs taken, the coastline mapped, the training completed, but the premature termination, the losses, and Byrd's enigmatic public statements created a narrative vacuum that has been filled over the decades by interpretations of varying credibility. Byrd himself returns to Antarctica one more time in 1955 to 1956 as part of Operation Deep Freeze, the American contribution to the International Geophysical Year of 1957 to 1958. This operation was smaller, more focused, and more explicitly scientific in its objectives. It established the permanent American research station at the South Pole, Amundsen Scott Station, and laid the groundwork for the sustained scientific presence that continues on the continent to this day. Byrd, by then in failing health, served in a largely ceremonial role. He died in 1957 at the age of 68, and his personal papers and diaries, while extensively studied, have never fully resolved the questions surrounding his earlier expedition. The International Geophysical Year itself was a remarkable undertaking, an 18-month period of coordinated global scientific research involving 67 nations and focused heavily on Antarctica, where 12 nations established over 50 research stations across the continent. The IGY produced an enormous volume of data on Antarctic meteorology, glaciology, geomagnetism and seismology, and it established the principle that Antarctica should be a zone of peaceful scientific cooperation, free from military activity and territorial dispute. This principle was formalized in the Antarctic Treaty, signed on December 1, 1959, by the 12 nations that had participated in the IGY, and it has governed the continent ever since. The treaty is, by any measure, an extraordinary document. It suspends all territorial claims without requiring any nation to renounce them. It prohibits military activity, nuclear testing, and the disposal of radioactive waste. It guarantees freedom of scientific investigation and mandates the sharing of research data. It establishes a system of mutual inspection, allowing any signatory nation to send observers to any research station on the continent at any time. And it has been maintained, renewed, and expanded over more than 6 decades. Surviving the Cold War, the collapse of the Soviet Union, and the rise of new geopolitical rivalries without significant challenge or violation. In the history of international law, there is nothing quite like it. No other agreement has succeeded in demilitarizing an entire continent. No other treaty has prevented resource extraction on a landmass known to contain significant mineral and fossil fuel deposits. No other international framework has maintained such a high degree of cooperation among rival nations for such a sustained period of time. The Antarctic Treaty is often cited as one of the greatest achievements of 20th century diplomacy, a model of what international cooperation can accomplish when the stakes are high enough and the political will is sufficient. And yet the very perfection of the agreement invites a question that is rarely asked in polite diplomatic circles. Why? Why did 12 nations, at the height of the Cold War, at a moment when mutual suspicion and ideological conflict were tearing the world apart, agree so readily to lock an entire continent away from exploitation, competition, and control? What made Antarctica so special, so uniquely deserving of protection, that nations willing to threaten each other with nuclear annihilation over Cuba, Berlin, and Korea were willing to cooperate unconditionally at the bottom of the world? The official answer is science. The spirit of the IGY, the recognition that Antarctica's value as a scientific laboratory outweighed its value as a strategic or economic asset. The enlightened self-interest of nations that understood the importance of preserving the continent for research. This answer is not wrong, but it is perhaps incomplete, because the treaty does not merely protect science. It restricts access. It limits what can be done, where and by whom. It places an entire continent, 14 million square kilometers of land, ice, and everything buried beneath them, under a regime of controlled investigation that has no parallel anywhere else on Earth. And controlled investigation by its nature means that some things are investigated and others are not. Some questions are funded and others are deferred. Some areas are surveyed and others remain blank. The treaty does not prohibit exploration, but it creates a framework within which exploration proceeds slowly, cautiously, and under the supervision of a community that has strong institutional reasons to maintain consensus and avoid controversy. In this framework, discoveries that challenge established models, discoveries like the fan-shaped basin province, like the hidden landscape beneath Wilkes Land, like the anomalous genetic signatures in Lake Vostok's accretion ice, are published, peer-reviewed and discussed, but they are rarely pursued with the urgency or the resources that their implications would seem to demand. The ice keeps its secrets, and the system that governs the ice for all its virtues is not designed to force those secrets into the light. It is designed to manage them, to release them gradually, carefully, in ways that do not disrupt the fragile consensus that holds the treaty system together. Whether this is wisdom or caution or something else entirely is a question that each observer must answer for themselves. But the question itself, the question of what is being managed and why, is one that grows louder with every new discovery, every new anomaly, every new whisper from beneath the ice. And among those whispers there is one that has puzzled geologists for nearly 70 years. A range of mountains buried beneath the ice as tall as the Alps, sitting in a place where no mountain should exist. Mountains that have no satisfactory explanation. Mountains that were discovered almost by accident and that have resisted every attempt to account for their presence in the heart of the most geologically stable region on Earth. In 1958, during the International Geophysical Year, a Soviet traverse team conducting seismic surveys across the interior of East Antarctica detected something that should not have been there. Beneath the ice, in one of the most remote and inaccessible regions of the continent, their instruments registered a series of strong seismic reflections, indicating the presence of a major mountain range. Peaks rising to heights of nearly 3,000 meters above the surrounding bedrock, buried under an ice sheet more than 3 kilometers thick. The team named the range after their colleague Grigory Gamburtsev, a Soviet geophysicist who had pioneered techniques for deep seismic surveying and who had died the previous year, never knowing what lay beneath the ice his methods would help reveal. The Gamburtsev subglacial mountains were, from the moment of their discovery, an anomaly. They were not small foothills or modest ridges of the kind that might form along the margins of a tectonic plate or in the wake of glacial erosion. They were a fully developed mountain range, comparable in scale to the European Alps, with jagged peaks, deep valleys, and a topographic profile that suggested they had not been significantly eroded since their formation. And they were sitting in the middle of a craton, one of the oldest and most geologically stable pieces of continental crust on Earth. This is the problem. Mountains, in the conventional understanding of geology, are formed by specific process, and those processes leave identifiable signatures. The most common mechanism is plate collision. When two tectonic plates converge, the crust is compressed, folded, and thrust upward, creating mountain ranges along the boundary. The Himalayas were formed this way by the collision of the Indian and Eurasian plates. The Andes were formed by the subduction of the Nazca Plate beneath the South American plate. The Alps were formed by the collision of the African and European plates. In each case, the mountains sit along a plate boundary or a zone of active tectonic deformation, and their age, composition and structure reflect the forces that created them. The Gamburtsev Mountains sit in none of these contexts. They are located near the centre of the East Antarctic craton, hundreds of kilometres from the nearest plate boundary, in a region that has not experienced significant tectonic activity for hundreds of millions of years, possibly more than 1 billion. Cratonic crust is, by definition, old and stable. It forms the deep roots of continents, the ancient nuclei around which younger rock accumulates. It does not, as a rule, produce mountains. And yet, beneath the ice of East Antarctica, there they are. 3,000 masts of unexplained elevation, sitting in a place where the geology says they should not exist. The initial Soviet surveys provided only a rough outline of the range. The technology of the 1950s was sufficient to detect the mountains, but not to image them in detail. It was not until 2008 to 2009 that a comprehensive survey was conducted as part of an international collaboration called AGAP, the Antarctica's Gamburtsev Province Project. Using airborne ice-penetrating radar, gravity measurements, and magnetic surveys, the AGAP team produced the first detailed three-dimensional image of the Gamburtsev Mountains, and what they found deepened the mystery rather than resolving it. The mountains were sharp, not the rounded, worn profiles of ancient ranges that have been ground down by hundreds of millions of years of erosion, but the angular, steep-sided peaks of a range that appeared almost young. This was puzzling because every line of evidence indicated that the mountains were very old, possibly dating to the Proterozoic Eon, more than 500 million years ago, and possibly much older. Radiometric dating of the few rock samples that could be linked to the range through glacial erratics, rocks transported from their place of origin by moving ice and deposited elsewhere, suggested crustal roots extending more than 1 billion years into the past. The mountains were ancient, but they did not look ancient. They looked preserved. The leading hypothesis, developed by the AGAP team and published in a series of papers in Nature and other journals, proposed a two-stage origin. In this model, the original Gamburtsev range formed during the assembly of the Gondwana supercontinent, roughly 500 to 600 million years ago, when tectonic forces compressed the crust and created a mountain belt in the interior of the assembling landmass. Over the following hundreds of millions of years, this original range was eroded down to a low, flat peneplain, a featureless surface of the kind that typically forms when ancient mountains are worn away to their roots. But then, sometime in the Cretaceous or early Cenozoic, roughly 100 to 60 million years ago, the roots were reactivated. Thermal processes in the mantle beneath the craton heated the crust from below, causing it to expand and rise. Ancient fault lines were reopened. The old eroded mountain roots were pushed upward again, like a dormant volcano stirring beneath a plain, and a new range formed along the lines of the old one, not through fresh tectonic collision, but through the resurrection of structures that had been lying dormant for 500 million years. This hypothesis is elegant, and it accounts for many of the observed features: the ancient root ages, the relatively youthful topography, the location within a stable craton, but it has not been universally accepted. Some researchers have questioned whether the thermal uplift mechanism is sufficient to produce mountains of the Gamburtsev scale, noting that similar processes elsewhere on Earth have produced plateaus and gentle swells but not alpine-scale peaks. Others have pointed out that the sharp topography of the range may be a product of preservation rather than youth, that the ice sheet which has covered the mountain since the onset of Antarctic glaciation may have protected them from the erosion that would normally have worn them down, just as it preserved the river valleys in Wilkes Land and the fan-shaped basin province beneath the broader ice sheet. In this view, the mountains are not young at all. They are old mountains that have been kept in a state of suspended animation by the ice, their edges unblunted, their peaks unsoftened, their profiles frozen in the shape they held when the ice first arrived. If this is correct, if the Gamburtsev Mountains have been preserved essentially unchanged for 34 million years or more, then they represent yet another layer of the Antarctic archive, not just a geological structure, but a snapshot of a moment in time, a mountain range that looked the same on the day the ice closed over it as it does today beneath 4 kilometers of frozen water. The only thing that has changed is that it's been removed from view, placed beyond the reach of wind and rain at the slow, patient chemistry of weathering that wears down every other mountain range on the surface of the Earth. There is something deeply strange about a mountain range that exists in secret. Mountains are, by their nature, visible. They are the most prominent features of a landscape, landmarks, barriers, weather makers, the bones of the Earth thrust into the sky. Every culture that has lived near mountains has named them, mapped them, built stories and mythologies around them. The Himalayas are the abode of gods, the Andes are the spine of a continent. The Alps have shaped the political and cultural geography of Europe for millennia. But the Gamburtsev Mountains have never been seen by any living thing, not by a human being, not by an animal, not by a plant. They have existed, for longer than the human species has existed, in absolute and total darkness, their peaks pressing upward against a ceiling of ice that they will never penetrate, and yet they are not inert. The AGAP surveys revealed that the Gamburtsev Mountains play a critical role in the dynamics of the East Antarctic ice sheet. The range acts as a topographic barrier, dividing the flow of ice into separate drainage basins. Water from melting at the base of the ice collects in the valleys between the peaks, forming subglacial lakes and streams that drain toward the coast through channels carved by the mountain's own geometry. The mountains are, in a sense, still functioning as mountains, directing the flow of water, shaping the movement of ice, influencing the climate of the continent, even though they are invisible and inaccessible. This hidden influence raises a question that connects the Gamburtsev Mountains to every other anomaly beneath the Antarctic ice. If a mountain range of alpine proportions can exist beneath the ice without being detected for millions of years, if it can shape the behaviour of the ice sheet, direct the flow of subglacial water, and influence the geology of an entire continent, all without ever being seen, then what else might be exerting a hidden influence from beneath the surface? The fan-shaped basin province was not discovered until 2026, despite decades of radar and gravity surveys. The hidden landscape in Wilkes Land was not identified until 2023, despite the data being available for years before anyone thought to analyse it in the right way. the subglacial lakes were not confirmed until the 1990s, despite being hypothesized in the 1960s. Each discovery has expanded the map of the unknown, revealing not just new features but new categories of features, things that no one had imagined were there, hiding in plain sight beneath the most surveyed ice sheet on the planet. The Gamburtsev Mountains are a reminder that the absence of evidence is not evidence of absence. They are a reminder that what we do not see can be as large, as important, and as consequential as what we do. They are a reminder that Antarctica, for all the treaties, the research stations, the satellite surveys, and the decades of scientific investigation, remains at its core unknown. But there is one more layer to this story. One more discovery that shifts the ground beneath everything else. Because the ice that covers Antarctica is not eternal. It has advanced and retreated before, and in the geological record there is evidence that the Great Thaw may have already happened, that the ice sheet, or at least a significant portion of it, collapsed at some point in the past, exposing the land beneath for a period long enough to leave traces that can still be detected today. And if it happened before, under natural conditions, then the question is no longer whether it can happen again, but when, and what will be revealed when the ice finally releases its grip on the land it has held for 34 million years. The assumption that the East Antarctic ice sheet has been permanent, that it formed 34 million years ago, and has remained essentially intact ever since, is one of the foundational beliefs of modern glaciology. It is a belief rooted in logic, in observation, and in the sheer physical enormity of the ice itself. The East Antarctic ice sheet contains roughly 21.5 million cubic kilometres of frozen water. Its base, in many places, is frozen solid to the bedrock beneath, held in place by temperatures so far below zero that the concept of melting seems almost absurd. The ice at the centre of the sheet has been there so long that the bedrock beneath it has been depressed by more than a kilometre under its weight. Everything about the East Antarctic ice sheet suggests permanence, stability, immovability. It is the most massive single object on the surface of the Earth, and it has been treated, in most climate models and geological reconstructions, as a constant, a fixed feature of the planet's geography that might fluctuate at its margins, but would never fundamentally change. This assumption is now being questioned, not by fringe theorists or alarmists, but by the sediment record itself, by evidence drawn from the ocean floor around Antarctica, from the chemistry of ancient marine organisms, and from the behaviour of the ice in regions where it was once thought to be most secure. The evidence does not prove that the East Antarctic ice sheet has collapsed in the past, but it suggests with increasing clarity that it has retreated, significantly, repeatedly, and in ways that expose portions of the continent that have been assumed to be permanently buried. The most direct evidence comes from marine sediment cores drilled near the Wilkes Land coast, the same region where Jameson's team discovered the hidden river landscape beneath the ice. In 2017, a study published in Nature examined sediment cores recovered during the Integrated Ocean Drilling Program, and found layers of terrestrial material, land-derived sediment, including clay minerals and organic matter, interspersed with the usual marine deposits. The presence of terrestrial sediment in ocean cores is significant because it indicates erosion of exposed land surfaces that under normal conditions would be covered by ice. The layers containing this terrestrial material were dated to the Pliocene epoch, roughly 3 to 5 million years ago, a period when global temperatures were 2 to 3 degrees Celsius warmer than present and atmospheric CO2 levels were roughly 400 parts per million, a concentration that the modern atmosphere has already reached. The implication is stark. During the Pliocene, with temperatures only slightly warmer than today and CO2 levels comparable to those of the 21st century, significant portions of the East Antarctic ice sheet may have melted. Not the entire sheet, and the evidence does not support a complete collapse, but enough to expose coastal and near-coastal regions of the continent, including areas that have been assumed to be permanently glaciated. The sediment record suggests episodic retreat and re-advance, a pattern of instability that is inconsistent with the image of the East Antarctic ice sheet as an immovable monolith. The ice has been there for 34 million years, yes, but it has not been there uniformly, continuously and without interruption. There have been moments, perhaps lasting thousands of years, perhaps longer, when the ice pulled back and the land beneath it was exposed to the sky for the first time in millions of years. And this is where the Wilkes Land subglacial basin becomes critical. Beneath the ice in this region lies not only Jameson's hidden landscape, but also a feature that glaciologists have come to regard with growing concern. A massive subglacial basin, hundreds of kilometres across, where the bedrock sits well below sea level. This basin is, in effect, a bowl, a depression in the rock that is currently filled with ice, but that, if the ice were to retreat past a certain threshold, could be invaded by ocean water. Once seawater reaches the base of an ice sheet grounded below sea level, it accelerates melting from below, destabilizing the ice and triggering a feedback loop that can lead to rapid, irreversible collapse. This process, known as marine ice sheet instability, is well documented in the West Antarctic ice sheet, where several major glaciers are already showing signs of accelerating retreat. But it has generally been assumed not to apply to East Antarctica, where the ice is colder, thicker and more firmly grounded. The Wilkes Land basin challenges that assumption. A study published in Nature of Climate Change in 2014 identified what the authors called an ice plug, a relatively narrow band of ice along the coast that holds back the vast volume of ice filling the basin behind it. If this plug were to be removed, by warming ocean water undercutting it from below, or by surface melting weakening it from above, the ice behind it could begin to flow outward into the ocean in a process that would be difficult or impossible to reverse. The volume of ice contained in the Wilkes Land basin is sufficient, if fully discharged, to raise global sea levels by 3 to 4 metres. Not over millennia, over centuries, possibly less, depending on the speed of the collapse. 3 to 4 metres of sea level rise would redraw the coastline of every continent on Earth. It would inundate cities Miami, Shanghai, Mumbai, Amsterdam, Bangkok, New York. It would displace hundreds of millions of people. It would destroy infrastructure, contaminate freshwater supplies, and trigger economic disruptions on a scale that no modern society has ever experienced. And it could be triggered by the loss of a single ice plug in a single basin on a continent that most people never think about. But the potential for catastrophic sea level rise is not the only consequence of an East Antarctic retreat. There is another consequence, one that is rarely discussed in the climate literature, but that connects directly to everything that has been buried beneath the ice for 34 million years. If the ice retreats, if it pulls back from the coastline, if it thins over the subglacial basins, if it exposes the hidden landscape and the ancient sediments and the sealed lakes and the fan-shaped province and the Gamburtsev mountains, then all of those things, preserved in their frozen archive for an almost inconceivable span of time, would be exposed to the surface environment, to air, to water, to sunlight, to erosion, to the same forces that have shaped and reshaped every other landscape on the planet for hundreds of millions of years. The archive would begin to degrade. The river valleys, preserved in perfect detail for 34 million years, would be weathered and eroded within centuries. The sediments, containing whatever organic and chemical records they hold, would be washed into the sea. The subglacial lakes, sealed for millions of years with their unique biospheres and their accumulated chemical histories, would be drained or diluted. The Gamburtsev mountains, protected from erosion since before the first primates walked the earth, would begin to wear down, their sharp peaks softening, their valleys filling with debris. Everything that the ice has kept would be lost, not to a sudden catastrophe, but to the ordinary relentless processes of a world without ice. There is a terrible irony in this. The same warming that might make it possible to access Antarctica's secrets, to drill deeper, survey more broadly, explore regions that are currently too remote and too ice-bound to reach, could also destroy those secrets before they can be read. The ice is both the barrier and the guardian. It prevents us from seeing what lies beneath, but it also preserves what lies beneath in a condition that would be impossible to maintain once the ice is gone. The moment of revelation would also be the moment of destruction. The opening of the vault would be the beginning of the end of whatever the vault contains. This is not an abstract concern. The warming of the Southern Ocean is already measurable. Circumpolar deep water, warm saline water from the mid-depths of the ocean, is intruding onto the continental shelf around Antarctica in increasing volumes, driven by changes in wind patterns and ocean circulation linked to global climate change. This warm water is reaching the bases of ice shelves and coastal glaciers, accelerating melting in regions that were previously stable. The process is slow by human standards, measured in millimeters of thinning per year, in kilometers of grounding line retreat per decade, but it is accelerating and the trajectory is clear. The ice is losing mass, the margins are retreating, the system is moving incrementally but measurably toward a state that has not existed since the Pliocene, a state in which parts of Antarctica are exposed, the ice is diminished, and the world the ice has kept hidden for 34 million years is no longer entirely sealed. What will be found when that happens, if it happens, is impossible to predict with certainty. The radar surveys and seismic profiles and gravity maps have provided a sketch, a rough outline of what lies beneath. But a sketch is not a portrait. The hidden landscape of Wilkes Land, the fan-shaped basin province, the Gamburtsev Mountains, the subglacial lakes. These are features that have been detected remotely, through kilometers of ice, using instruments that can measure shape and density and reflectivity, but cannot tell us what the sediment contains, what the water chemistry reveals, what the organic residues might preserve. The details are still locked away, still sealed in the dark, still waiting for an investigation that may come too late, or that may arrive just in time to witness the beginning of their unravelling. And beneath all of this, beneath the science, the data, the projections, and the policy debates, there remains a deeper unease, a question that is not scientific but philosophical, a question about what it means to share a planet with something this old, this hidden, this fundamentally unknown. The ice has kept its secrets for 34 million years. That is longer than the entire evolutionary history of the great apes, longer than the existence of the grasslands that cover the continents, longer than the formation of the Himalayas. The world that the ice sealed away is not merely old. It is from a different epoch of planetary history, an epoch when the Earth was warmer, the atmosphere was different, the continents were in different positions, and life itself was following trajectories that led, eventually, to us, but that could just as easily have led elsewhere. Whatever is beneath the ice is not ours. It does not belong to our time. It belongs to a world that ended before we began, a world that was buried, preserved, and forgotten. And the question that haunts every researcher, every geophysicist, every glaciologist who has ever stared at a radar profile of the Antarctic bedrock is the same question that has haunted this continent since the first ship sighted its shores through the fog. Are we ready to remember what the ice was meant to forget? There is a place on the edge of East Antarctica where the ice meets the rock in a way that unsettles the usual categories. It is not a coastline, not a mountain front, not a glacial terminus in the ordinary sense. It is a gravity anomaly, a region where the pull of the Earth is measurably different from what the models predict, where the mass beneath the surface is distributed in a way that does not conform to the expected density of ice and rock and sediment. It sits beneath the Wilkes Land basin, roughly 500 kilometers inland from the coast, and it has been known to geophysicists since satellite gravity measurements first became precise enough to detect such features in the early 2000s. It is large, several hundred kilometres across, and it is deep, centred at a point well below the bedrock surface, suggesting a concentration of dense material buried far beneath the ice. And no one knows with certainty what it is. The most widely cited hypothesis is that it is the remnant of an asteroid impact, a buried crater, possibly 300 to 500 kilometres in diameter, created by a massive bolide strike sometime in the deep past. If this interpretation is correct, it would make the Wilkes Land anomaly one of the largest impact structures on Earth, comparable in size to the Chicxulub crater in Mexico's Yucatan Peninsula, which has been linked to the mass extinction that killed the non-avian dinosaurs 66 million years ago. The gravitational signature, a negative anomaly ringed by a subtle positive margin, is consistent with the pattern produced by large impact craters, where the initial excavation creates a low-density depression that is partially filled by the rebound of the underlying mantle and the collapse of the crater walls. A study published in 2006 by a team led by Ralph von Fries of Ohio State University first proposed the impact hypothesis based on gravity data from the GRACE satellite mission. Von Fries and his colleagues estimated that the impactor responsible for the anomaly could have been roughly 48 kilometers in diameter, a body large enough to deliver an energy release thousands of times greater than the Chicxulub impact. They suggested a possible connection to the Permian-Triassic extinction event, approximately 252 million years ago, the most devastating mass extinction in the history of life on Earth, during which more than 90% of all marine species and roughly 70% of terrestrial vertebrate species were annihilated. The Permian-Triassic extinction, often called the Great Dying, has long been attributed to massive volcanic eruptions in Siberia, the Siberian Traps, which flooded the atmosphere with carbon dioxide and sulfur, triggering runaway warming, ocean acidification, and global anoxia. But some researchers have argued that volcanism alone may not account for the speed and severity of the extinction, and that an impact event, either as a primary cause or as a contributing trigger, could help explain the pattern of devastation observed in the fossil record. The Wilkes Land anomaly has never been confirmed as an impact crater. The evidence remains circumstantial, a gravity signature, a location beneath kilometres of ice, and a temporal correlation that is suggestive but not conclusive. No drill core has reached the anomaly, no direct sample of the rock at its centre has been analysed, no shocked core or quartz, no iridium enrichment, no tektite field, the standard indicators of an asteroid impact, has been recovered from the site, because the site is buried under the deepest, most inaccessible ice on the planet. The anomaly exists as a shape in the data, a shadow in the gravity field, a question mark embedded in the crust of the Earth beneath a continent that yields its answers only reluctantly and only in fragments. But the possibility alone is enough to reshape the way one thinks about what lies beneath the Antarctic ice. If the anomaly is an impact crater, if a body 48 kilometers across struck the Earth at that location at some point in the past 300 million years, then the energy released would have been sufficient to vaporize thousands of cubic kilometers of rock, inject a global cloud of dust and aerosols into the stratosphere, trigger earthquakes and tsunamis on a planetary scale, and alter the chemistry of the atmosphere for centuries or millennia. The scar of such an event would be immense, not just the crater itself, but the ring of shattered rock surrounding it. The layers of impact melt and fall back breccia, the deformed strata beneath the crater floor, recording the instant when the crust was punched downwards by a force beyond anything the Earth generates on its own. And all of this, the entire record of one of the most violent events in the history of the planet, would be sitting beneath the ice, preserved in the same frozen archive that has kept the river valleys, the mountains, and the lakes in a state of suspended time. The connection between the Wilkes Land gravity anomaly and the Great Dying remains one of the most tantalizing and unresolved questions in planetary science. The timing is uncertain, The size is estimated, not measured. The very nature of the anomaly, impact crater, tectonic feature, or something else entirely was there, is still debated. But the debate itself illuminates a broader truth about Antarctica that is easy to overlook in the day-to-day accumulation of data and analysis. This continent is not merely a storage vault for old landscapes and extinct ecosystems. It may be a repository of catastrophe, a place where the evidence of events that reshaped the entire biosphere of the Earth has been preserved intact and unread beneath an ice sheet that has been acting as the planet's memory for longer than any other geological feature on its surface. And the memory is not limited to the single events. The sediments beneath the ice, the layers of rock and soil and organic material that accumulated over hundreds of millions of years before the ice arrived, contain a continuous record of the processes that shape the continent and the planet. Volcanic eruptions, climate shifts, evolutionary radiations and mass extinctions, the assembly and breakup of supercontinents, the opening and closing of ocean gateways, the rise and fall of atmospheric carbon dioxide over timescales that make the modern climate debate seem like a footnote. All of this is encoded in the rock beneath the ice, in mineral compositions and isotope ratios and fossil assemblages that have never been exposed to the surface, never been sampled, never been analysed. The frustration of Antarctic science is that the archive is known to exist but cannot be fully accessed. Every indirect measurement, every radar profile, every gravity map, every magnetic survey all confirms that the bedrock beneath the ice is rich with information. But indirect measurements can only tell us so much. They can map the shape of the land. They can detect anomalies in density and composition. They can identify the boundaries between different types of rock. But they cannot read the fine print. They cannot tell us what species of pollen are preserved in a sediment layer 3 kilometers beneath the surface. They cannot determine the isotopic composition of a mineral grain trapped in a subglacial river deposit. They cannot reveal whether the organic molecules in a buried lake bed are the remnants of a forest floor or the metabolic byproducts of an unknown microbial community. For that level of detail, direct sampling is required, and direct sampling in the Antarctic interior remains one of the most technically challenging undertakings in the history of science. The challenge is not merely logistical, though the logistics are formidable. It is also institutional. The Antarctic Treaty System, for all its admirable qualities, creates a framework in which large-scale, high-risk scientific projects require international consensus, multi-year planning, and the coordination of resources across multiple national programs. Drilling to the base of the ice sheet in the interior of East Antarctica, through 3 or 4 kilometers of ice, into bedrock that has not been touched by any tool in the history of humanity, would require years of preparation, hundreds of millions of dollars in funding, and the development of drilling technologies that do not yet exist in a form suitable for deployment in the most extreme environment on Earth. Such a project has been proposed in various forms by researchers in Europe, the United States, and Australia. But it has never been funded at the scale required to proceed. The political will, the financial commitment, and the institutional courage needed to undertake such an endeavour have not yet converged. And so the archive waits. The crater, if it is a crater, sits in the dark. The sediments, if they contain what the indirect evidence suggests, remain unread. The mountains stand in silence. The lakes circulate their ancient water in loops that no one has traced. And the ice, indifferent to the questions asked above it, continues to do what it has done for 34 million years. It covers, it preserves, it conceals. Not with intent, not with purpose, but with an efficiency that no human archive has ever matched, and no human institution has ever rivaled. The question is whether the next generation of Antarctic science will have the resources, the ambition, and the freedom to open the archive before the ice itself decides the matter. Because the ice is not waiting for permission, it is responding to forces that are already in motion, forces that operate on timescales shorter than political cycles, shorter than funding horizons, shorter than the institutional memory of the treaty system. The Southern Ocean is warming, the circumpolar winds are shifting, the margins of the ice sheet are losing mass at rates that were not predicted even a decade ago. The vault is not as secure as it once was, and what emerges from it, whether by human investigation or by the slow, irreversible retreat of the ice itself, will not be a gentle revelation. It will be a reckoning with a past that is older, stranger, and more consequential than anything the frozen surface has ever suggested. There is a word that recurs in the scientific literature on Antarctica, used so frequently that its weight has been dulled by the repetition. The word is unprecedented. Unprecedented warming, unprecedented ice loss, unprecedented retreat of glacial margins. It appears in paper after paper, report after report, press release after press release, each time carrying the same unstated admission that what is happening now was not foreseen, that the models did not predict it, that the system is behaving in ways that the accumulated knowledge of the past century did not prepare anyone to expect. And when a field of science reaches for the word unprecedented with such regularity, it is worth pausing to consider what that word actually means. It means without such a precedent. It means outside the range of known experience. It means that the framework within which the observations were supposed to make sense is no longer adequate, and that something is happening that requires a new framework, one that has not yet been built. The East Antarctic ice sheet was supposed to be the stable one. This was the consensus that held for decades the reassuring counterpoint to the more alarming observations coming from the west side of the continent. West Antarctica, smaller, warmer, with much of its ice grounded below sea level, was always understood to be vulnerable. Its major glaciers, Pine Island and Thwaites, have been retreating for years, their grounding lines pulling back as warm ocean water intrudes beneath the ice shelves that hold them in place. Thwaites, in particular, has become a symbol of climate anxiety. A glacier the size of Florida, often referred to as the Doomsday Glacier, whose complete collapse could raise global sea levels by more than 60 centimetres on its own and destabilise neighbouring glaciers enough to add several metres more. The dynamics of West Antarctic ice loss have been studied extensively, modelled repeatedly, and debated publicly for more than a decade. The West is where the danger is, the narrative went. The East is too cold, too thick, too ancient to be at risk. That narrative is eroding. Not dramatically, not with a sudden cracking of an ice shelf or the carving of a city-sized iceberg, but in the quiet accumulation of data points that, taken together, describe a pattern that was not supposed to emerge. Satellite measurements from the GRACE and GRACE-FO missions, which track changes in the Earth's gravitational field caused by the redistribution of mass on the surface, have detected measurable ice loss in several sectors of East Antarctica, including the Wilkes Land region and the Totten Glacier system, which drains one of the largest subglacial basins on the continent. The losses are small compared to those in West Antarctica, tens of billions of tons per year rather than hundreds of billions, but they are accelerating, and they are occurring in regions that were previously assumed to be gaining mass through increased snowfall. The Totten Glacier is of particular concern. It is the primary outlet for the Aurora subglacial basin, a deep depression in the bedrock of East Antarctica that, like the Wilkes Land basin, sits well below sea level. The basin contains enough ice to raise global sea levels by more than 3 meters if fully discharged. And recent studies have shown that warm ocean water is already reaching the base of the Totten ice shelf, the floating extension of the glacier that braces it against the continental shelf and slows its flow toward the sea. Measurements taken by Australian and international teams using autonomous underwater vehicles and oceanographic moorings have detected circumpolar deep water at temperatures well above freezing, penetrating the cavity beneath the ice shelf melting it from below at rates that exceed the capacity of snowfall to replenish the lost mass. The grounding line of the Totten Glacier, the point where the ice lifts off the bedrock and begins to float, has been retreating, intermittently but measurably over the past 2 decades. The physics of what happens next are understood in principle, if not in precise timing. If the grounding line retreats far enough into the Aurora Basin, it will reach a point where the bedrock slopes downward into the interior of the continent, a reverse slope that makes the ice sheet inherently unstable. On a reverse slope, the ice is thicker further inland, which means the rate of ice discharge increases as the grounding line retreats, which causes the grounding line to retreat further, which increases discharge further, in a self-reinforcing cycle that can continue until the entire basin is emptied. This is the marine ice sheet instability mechanism, and it is the same process that is believed to be driving the accelerating retreat of the Thwaites Glacier in West Antarctica. The difference is scale. The Aurora Basin is larger than any single basin in West Antarctica. Its ice volume is greater. Its potential contribution to sea level rise is larger, and its collapse, if it occurs, would not only redraw coastlines around the world, but would also begin to expose the very bedrock, the very sediments, the very archive that has been sealed beneath the East Antarctic ice sheet for 34 million years. This is the convergence that makes the Antarctic story so urgent and so strange. The scientific desire to understand what lies beneath the ice, to read the archive, to access the sediments, to sample the subglacial lakes, to determine whether the Wilkes Land gravity anomaly is an impact crater or something else, is on a collision course with the climatic forces that may, within the span of a few human generations, begin to expose those same features through the uncontrolled retreat of the ice itself. The controlled investigation that researchers have been planning and proposing for decades, the deep drilling projects, the subglacial lake access missions, the comprehensive seismic surveys of the continental interior, may be overtaken by events. The ice may open the archive on its own terms, not in the careful, methodical fashion of a scientific excavation, but in the chaotic, irreversible fashion of a system in collapse. And what would be exposed would not simply be rock and sediment, it would be biology. The subglacial lakes are sealed for millions of years, harbour communities of microorganisms that have evolved in total isolation from the rest of the biosphere. If the ice retreats and the lakes are breached, not by sterile drill systems designed to prevent contamination, but by meltwater and ocean water carrying surface organisms into the subglacial environment, the consequences for those isolated ecosystems would be catastrophic. Species that have existed nowhere else on Earth, that have adapted to conditions of absolute darkness, extreme pressure, and chemical isolation, would be overwhelmed by organisms from the surface world, their unique biochemistry diluted, their evolutionary heritage erased before it could be studied. The biological archive would be destroyed at the moment of its exposure, like a manuscript crumbling to dust when the sealed chamber containing it is finally opened to the air. There is also the question of what the thawing sediments themselves might release. Permafrost in the Arctic, ground that's been frozen for thousands to tens of thousands of years, is already yielding surprises as it thaws. Ancient viruses preserved in frozen soil have been revived in laboratory settings, raising questions about the potential for pathogens from the deep past to re-enter the biosphere as permafrost melts. In Siberia, a 30,000-year-old giant virus, Pythovirus sibericum, was recovered from permafrost and shown to be still infectious, capable of infecting amoeba in the laboratory. Other ancient viruses have since been recovered from similar sources, demonstrating that the capacity for biological preservation in frozen ground is far greater than previously assumed. If Arctic permafrost, frozen for tens of thousands of years, can preserve viable microorganisms, then the question of what might be preserved in Antarctic ice and sediments, frozen for millions of years, is not merely academic, It is a question with direct implications for public health, for biosecurity, and for the fundamental understanding of how life persists across geological time. The ice is not just a geological archive, it is a biological one, and the biological archive, like the geological one, is now subject to forces that are moving it toward exposure, forces that are driven not by scientific curiosity, but by the chemistry of the atmosphere, the warming of the oceans, and the slow, accelerating response of a system that has been stable for longer than the human species has existed, but that is now, for the first time in millions of years, beginning to change. The change is not hypothetical, it is measured, it is documented, it is published in journals and tracked by satellites and discussed at conferences and summarized in reports that sit on the desks of policymakers who may or may not read them. The question is no longer whether the ice will retreat. The question is how far, how fast, and what will be left when it does. The archive is real, the threat to the archive is real, and the window of time in which it might be possible to read the archive before it is destroyed, to learn what the ice has been keeping before the ice gives it up on its own terms, is not infinite. It is closing, not with a sound, not with a warning, but with the slow, patient indifference of a process that has no interest in what lies beneath it and no memory of what it has been protecting. The ice does not know what it holds. It does not care what it covers. It simply responds to the temperature of the world around it, and the temperature of the world around it is rising. What lies beneath will not remain beneath forever. The question is whether it will be uncovered by the careful hands of those who wish to understand it, or by the careless forces of a climate that has no use for archives, no respect for secrets, and no patience for the 34 million years of silence that the ice has so faithfully maintained. The continent does not speak. It has never spoken. In the long registry of places that have shaped the human story, the fertile crescents where agriculture began, the river valleys where cities rose, the coastlines where empires launched their ships, Antarctica has no entry. No civilization has ever taken root on its surface. No mythology has grown from its soil. No language carries within it the memory of Antarctic seasons, Antarctic rivers, Antarctic skies. For as long as there have been human beings on this earth, Antarctica has been silent, a white vacancy at the edge of every map, defined not by what it contains but by what it withholds. And yet beneath that silence, beneath the weight of ice that has pressed down upon it for an age that dwarfs every human calendar, there is a record so vast, so detailed, so achingly preserved that it may contain more of the Earth's history than all the libraries, all the archives, all the monuments and inscriptions of every civilization that has ever existed combined. This is the paradox that lies at the heart of the Antarctic mystery. The most uninhabited continent on the planet may be the most important. The place where no one has ever lived may hold the key to understanding the deepest patterns of life itself, its origins, its resilience, its fragility, its capacity to endure through catastrophes that would seem, from the human vantage, to be absolute. The forests that once grew where now there is only ice were not marginal. They were part of a global system, connected by ocean currents and atmospheric circulation to every other forest, every other ecosystem, every other living thing on the surface of the earth. When they were buried, the system did not simply lose a component. It lost a memory, a record of how that component functioned, how it responded to change, how it died. And that memory, sealed in sediment and ice and the dark water of subglacial lakes, is still there, waiting, not for rescue, not for redemption, simply waiting, the way stone waits, the way water waits, the way everything that is old enough eventually stops anticipating and simply persists. There is a tendency in the modern world to treat the deep past as irrelevant, as a curiosity, a diversion, a subject fit for museum exhibits and documentary films, but not for serious engagement with the present. The future is what matters. The next quarter, the next election, the next technological breakthrough, the next crisis. The past is settled. The past is known. The past is behind us. But the past is not behind us. The past is beneath us, is beneath the ice of a continent that sits at the bottom of the world, and it is rising, some Muhammad saying, not metaphorically, but physically, in the form of data and sediment and meltwater and radar returns that are slowly, inexorably forcing a revision of what we thought we knew about this planet and its history. The fan-shaped basin province, with its 30 radiating basins carved by forces that predate the breakup of Gondwana, tells us that the geological history of Antarctica is not the simple, stable narrative that was assumed for generations. The hidden landscape of Wilkes Land, with its perfectly preserved river valleys and floodplains, tells us that the transition from a living continent to a frozen one was swift, violent, and total, and that the evidence of what was lost has been kept in a state of preservation unmatched anywhere else on Earth. The Gamburtsev Mountains, with their alpine peaks buried beneath kilometres of ice in a region where no mountains should exist, tell us that the processes shaping this continent are deeper, older, and more mysterious than the textbooks suggest. The subglacial lakes, with their sealed water and their isolated biology, tell us that life finds ways to persist in conditions that would seem to preclude it, and that the tree of life may have branches that no one has yet seen. The gravity anomaly beneath Wilkes Land, whether it is an impact crater or something else, tells us that the history encoded in the Antarctic bedrock may include events of planetary significance, events that reshaped the biosphere and altered the course of evolution in ways that are still being unravelled, and the ice itself, the ancient air trapped in its bubbles, the dust particles caught in its crystal lattice, the chemical signatures layered in its depth, tells us that the atmosphere of the Earth has a longer and more complex history than any single ice core has yet been able to capture. 3 million years of stable greenhouse gases recorded in the blue ice of Allen Hills. 34 million years of frozen silence sealing away the memory of a world that breathed differently, circulated differently, lived differently than the one we inhabit now. And somewhere below the deepest ice, in layers that no drill has reached and no instrument has measured, there may be air from the very first years of the Great Freeze, the last breath of a continent that was about to go silent for an age that has not yet ended. What does it mean to share a planet with a secret this large? What does it mean to walk on a world whose oldest continuous memory is locked beneath a place that no human hand has touched, no human eye has seen, no human voice has named? The Antarctic ice sheet is not a wall. It is not a barrier. It is a threshold, a boundary between the known and the unknown, between the present and the deep past, between the world as we have constructed it and the world as it was before we existed. And thresholds by their nature are places of transition. They are not meant to be permanent. They are meant to be crossed. The crossing has already begun, not with a single bold step, not with a proclamation or a treaty or a mission statement, but with the slow, diffuse pressure of a warming atmosphere, a changing ocean, a shifting wind. The ice is responding. It is thinning at its margins, retreating from its coastlines, losing mass from basins that were supposed to be inviolable. The process is measured in millimeters and gigatons, in fractions of a degree and fractions of a century. But it is cumulative, it is directional, and it is, by every available measure, accelerating. What will be found when the threshold is fully crossed, when the ice recedes far enough to expose the land beneath, the sediment beneath the land, the water beneath the sediment, the rock beneath the water, is a question that no living person can answer. The archive is too large, too old, too deeply buried for prediction. It may contain exactly what the model suggests, river sediments, mineral deposits, microbial communities, atmospheric records. It may contain things that no model has anticipated, traces of processes, events, or conditions that fall outside the current framework of understanding. It may contain nothing more than stone and silence, or it may contain something that changes the way humanity understands its own place on this planet, its age, its fragility, its smallness in the face of a history that stretches back not thousands, not millions, but tens of millions of years into a past that was not waiting for us, that did not need us, and that persisted in the dark long before the first human thought was ever formed. The ice holds everything. The ice reveals nothing. And somewhere between those two truths, between the holding and the revealing, between the silence and the sound, between the frozen and the thawing, there is a continent. Not the one on the maps, not the white featureless blank that fills the bottom of every globe and every atlas and every satellite image. The other one, the one beneath, the one that lived and breathed and grew forests and carried rivers and hosted creatures that walked beneath skies no one remembers. The one that was sealed away before history began and that has been waiting in perfect darkness for 34 million years. Not for discovery, not for understanding, not for any human purpose at all. Simply waiting, the way the earth has always waited. Patient, indifferent, and immeasurably old.